So let's get started with the June 2004 Regents Chemistry Test Review. And let's get started with the first section, okay, which is Part A, and that's going to be 30 questions, multiple choice, the easier of the multiple choice, so they say. And let's get to the first question. Compared to the charge of a proton, the charge of an electron has. Okay, these choices are about the size of the charge. Now you probably already know that an electron is negatively charged and a proton is positively charged, and the number of protons and electrons are equal in atoms that are basically always neutral. Okay, for instance, if I was to have aluminum, we say aluminum is an atom, and you say atom, I say neutral. Neutral. You say atom, neutral. Okay, it's like a dance party. Any case, we know that in redox, anytime you have an atom hanging out, we give it a zero charge. Now why? Well, because it is neutral. Its atomic number 13, so it has 13 protons. And if it's neutral, each proton would have positive 13. Therefore, we need 13 electrons. Okay, and that would make the whole thing neutral. So electrons being negative, protons being positive, all of that would give you a neutral atom, as all atoms are. Atoms are always neutral. You say atom, I say neutral. Now, so if you didn't remember that and you needed some place to look, a great place to remind yourself about the magnitude of charge, and the opposite, of course, would be table O. Let's go there. So in table O, we have the proton. Okay, we have the proton and we have an electron. Although it's not listed there, a beta particle is essentially the same thing as an electron. Okay, although it's really an electron that comes out of a nucleus, which is discussed in your nuclear chem part of the class, you can treat the beta particle as an electron. So looking carefully, you'll see the mass number, as you probably remember, is a top number is a 0. We give the electron a mass number of 0, and its charge number is -1. Look at a proton, okay, it's given a hydrogen symbol because hydrogen, if you remember, is 1/1. It has 1 proton, and if it's an atom, it has 1 electron. Okay, now when you lose an electron, you're just going to have the proton remaining. Okay, because 1 minus 1 gives me 0 neutrons. Just giving you a lot of things to think about here. So in any case, the mass number is 1 for the hydrogen, and its charge is +1. So if you look very carefully, okay, you can see that the beta particle, or the electron, and the hydrogen, very similar, okay, very similar, but they differ because they have opposite magnitudes of charge. The bottom number is -1 here, the bottom number here is +1. So they have opposite charges and they're equal in magnitude. So another place to look if you needed to see that. Let's go back to the question. So choice 1 is definitely 4. They have the same magnitude of charge because one is what? +1. Okay, this is -1, but they have opposite signs. Whether you can see that from understanding the concept that atoms are neutral, or from table O, number 1 is 4. Number 2. All right, so number 2, and if you notice, we're in the atomic structure of this test, and they usually go somewhat in order from atomic structure on. Number 2, which atom has the largest atomic radius? So what they're asking here is which atom has electrons, or at least its outermost electron, that is farthest from its nucleus, that's positive. Of course, that's the nuclear charge due to protons. Now you can go directly to table S, or you can use your understanding of the periodic trends. And you should know, as you go down a column, the atoms get bigger because of either the fact that you're adding extra shells of electrons, or the idea that there's some more shielding of the inner core electrons from the outermost. So I'm going to do both for you. Let's go to the periodic table. If you notice, it's potassium, francium, cesium, and rubidium. These are all group 1 ions, are called alkali metals. So given these four, let's go see where they are on the periodic table. So here we are with your periodic table of elements, and we are down this column. So as you can see, we're dealing with potassium, rubidium, cesium, and francium. Now, if you didn't know that these symbols represented these elements, you can go to table S to see that. Okay, but we'll first start here. You should know as you go down any group, the size of the atom increases because, well, there are more shells of electrons. If you don't understand that, now I know that, okay, that means francium's the winner because it's got, what, more filled shells of electrons than cesium. Truth, francium is the winner because it's the bottom of the row. But I want you to understand that we can also say, I can ask you the same question and say, who is more metallic? Okay, who is more metallic? Well, you would say francium because it is bigger. Being a metal means your ability to lose electrons, and the bigger the atom, the easier to lose. So francium, based on your trends, is the biggest. And you should know, as an aside, going across, the nucleus gets what? Smaller, or as the radius, I should say, gets smaller as you go across. All right? So we know the nonmetals are the smaller as you go up and across. In any case, if you didn't like any of that, you can go to table S, and let's do that. So before we go to table S, I really wanted to show you that potassium has a 2-8-8-1. These are, of course, the number of electrons in each filled shell. So potassium is electrons that are occupying 4 different energy levels, or 4 different shells. Rubidium is 2-8-18-8-1. Okay, it's got 5, 1, 2, 3, 4, 5 electrons, or 5 shells, I should say. 5 places where electrons can go. So this has an extra shell. This has 4 and this has 5. Okay, and cesium would have 6 and so forth, as you can see. So having an extra shell of electrons makes the atom bigger. But I also mentioned that the more shells of electrons you have, the harder it is for this nucleus to overcome this negative forces it has to get through. Remember, the outermost electron, okay, is attracted by the positive force, the nucleus in the nucleus. So therefore, this electron force, this positive coulombic force, has to get through these shells. So the more filled shells you have, the harder it is for this electron to feel the nucleus. We call that an effective nuclear charge. Any case, so that's happening as well. So going on to table S. So as you look at table S, there's a lot of information here. First, ionization energy, electronegativity, melting point, boiling point, density, atomic radius. You can see I already have potassium as 200. Going down the alkalis, rubidium is 215. Going down even more, cesium is 238, and that's a trend you should have studied. And of course, francium is 242. So right off table S, a lot of information there. So of course, the large atomic radius, francium, choice 3. Number 3. In the wave mechanical model of the atom, an orbital is defined as, okay, the wave mechanical model, most students say, oh my gosh, what is going on here? The wave mechanical model is the current model, and it's got a couple of, I guess, synonyms. Wave mechanical model, the electron cloud model, current model. Any case, this model is under the understanding that, well, you should understand the previous models before we even get to discussing this. So let me just I messed up here. Let me just white out some places here so we can kind of make some notes and look at some things. Because a couple of choices here make you differentiate between a couple of different models that you are held accountable for. Okay, well, let's start with very simply, I'm not going to go through all the models here. You can look at different review videos that I have on this. But let's start with the Bohr model, which you should be very aware of. The Bohr model is a model essentially where we have protons and we have electron orbitals in distinct energy shells. But these electrons go in circular paths. Now, the reason I'm bringing up the Bohr model, although very important and influential, it was the first model to incorporate the idea of a quantized form of energy. Electrons can exist in distinct energy levels or shells, okay, from the nucleus out to the outermost edge. Now, in order for electrons to get there, they need an exact amount. That's why we said it's a quantized model. But what I want you to get from this is people always think, oh, the model. And this one's so studied, and everyone's heard of the Bohr model, and you've seen this written in so many textbooks. Everyone seems to fall for, oh, circular paths. Yeah, that's the way the electrons go. And of course, they do not work that way. And that's, of course, one is the limitation of the Bohr model is electrons do not travel this way. Although he was right that electrons exist in distinct orbits or with distinct energy levels, he was not correct that electrons orbited the nucleus like the planets do the sun. So that planetary model was part of the reason why the Bohr model kind of unraveled a little bit, although the work is still monumental. So people like to fall for the circular path because they've seen this so many places, and that's the Bohr model. That's not the current electron cloud model, the wave mechanical model. So we've got to get rid of 3 and 4. Now, what I want you to help you understand is because he did a lot correct, and it was still monumental that he quantized the atom, meaning he was the first to talk about electrons existing in specific energy shells using something called quantum leaps to go from, let's say, a more stable orbit to an unstable orbit that's farther away, and that's why you learn about excited states. They wanted to give him a lot of credit, the current model. So they later found that electrons actually had a lot of wave properties at their size, and that's the de Broglie work that was done there. But the point being was electrons can exist both as waves and particles. And you need to understand that that's what's going to be picked apart in the new model. So when you hear wave mechanical model, the current model, electron cloud model, electrons can exist as waves and or particles. That's called a duality of nature. Now, more importantly, in this question, they want to know what the region of space. Well, when it was the Bohr model, it was an orbit. And to give Bohr credit, they still used the orb. Instead of orbit, they go orbital. Okay, so that's something to remember. The Bohr model was circular paths, but to give him credit, they put the AL, and this represents a region of space where electrons are acting as a standing wave. For those that took in a more advanced course, an s orbital has a standing wave that's a circle, and an unhybridized p had that dumbbell shape. So those things to think about as you probably may have learned or touched upon those. So it's a region of space. Now, because electrons are acting as waves, where their position are is kind of undefined, and we're getting into some other principles of quantum mechanics. So we talk about not so much where one electron is, really can't talk about where a wave is either, but you talk about probability. Quantum mechanics or the wave mechanical model is about dealing with a high number of these particles and using statistics to figure out where their whereabouts are. So in any case, it's probability. So you hear the word probability to explain the behavior, ability, yep. And we talk about standing waves, and you hear the word orbital. Those are all your keys to understanding the wave mechanical model. So the region of space where the electron has a high probability to be found. So it's not going to be a proton location, so obviously it's going to be choice 2. So number 3 is 2, a region of the most probable electron location. These are standing waves based upon probability because electrons act as waves, and that's all the keys you need to understand for the wave mechanical model. Number 4. Here we go with a question that deals with exactly what I was talking about, and that is the Bohr understanding, okay, the first quantized view that we still held true today. So when an excited electron moves to the ground state, electron does what? So we're going to need some area again to make some notes. Now, an excited electron as you can probably guess, as anyone you've known to be excited, has high energy. Now, things in nature don't have high energy by themselves. They do so because they must have gained energy. And you need to understand that we have a nucleus that's positive, okay, in the Bohr model, all right, has protons, and then we're going to have these shells of electrons, and you learn them as the first shell having 2, the second shell, let's say, having 8, okay, and of course we're going to keep going. So these are circular orbits, okay, and what you should know is electrons that can exist close to the nucleus do so because they don't have as much energy, because they're being controlled by that Coulombic attraction. So electrons that are closer have lower energy, and you need to understand lower energy means stable. Stable is a word like, for instance, hopefully your parents, or that rock in the backyard, that big boulder. You can't move the rock, you can't change it because it needs so much energy. It's going to stay in that position for a long time. Electrons that exist closer to the positive protons can't move that much because they're so close. They feel this positive so much. So they're going to stay there unless you, guess what, add a lot of energy. Stability is tied with energy. Now, electrons that can exist farther away have higher energy because they can stay farther away. So we say these guys have higher energy, and because they have higher energy, usually things with energy do something with that energy, and if they're going to do something, they tend to be more unstable, and they're not going to stay in this position very long with this high energy if they're going to do something. So the question reads, an excited electron. Well, electrons that are excited are farther away from the nucleus. So somehow an electron must have gained energy and jumped away. And what they're talking about now is jumping back to the ground state. Now, ground state means the lowest energy state possible, or a what? More stable state. So you need to understand this is leaping back toward the nucleus. So to go back toward a lower energy position, you need to give off and emit energy, okay? And you should have learned that energy is emitted in the form of electromagnetic radiation, sometimes in the visible spectrum or light. You guys saw maybe the flame test lab. So you need to understand the electron gives off its extra energy because it had it when it was excited. And of course, it moves to a lower energy state or a stable state. And these are the transitions. To go away from the nucleus, you need energy to pull away. When you have this extra energy, you won't stay there very long and you jump back. That's vital for the understanding of this test. Choice 4 is the best choice. Moving back closer to a lower energy stable position, and this higher energy had to be emitted. 4 is choice 4. Number 5. Which polyatomic ion is found in the compound represented in the formula NaHCO3? Now, as I tell my own students, when you see a cluster of nonmetals, I always tell them, what the heck is that? Go to the what the heck is that table. And in this course, the what the heck table is table E. Okay, table E lists all of these nonmetal clusters of nonmetals that have a singular charge. So table E is where you'd go, okay? And we're going to find that sodium HCO3, okay, is made up of course, Na plus attracting an HCO3 ion, okay? So how do I identify that? Well, I see a metal. That metal's positive. This rest of these nonmetals are probably negative. Okay, but to find this cluster, let's go to table E because we need its name. Okay, table E in all of its glory. And we dealt with NaHCO3. So we're looking for a cluster, and there it is. And that is the hydrogen carbonate ion. So back to the question. So clearly, from reading what this cluster is, and hopefully you can be able to pull it apart, I took away the metal, that's positive part, and I took away this ion. So it's the hydrogen carbonate ion from table E. Now, what I will say is, what they love to ask about is that what kind of bonds does this compound have? And you should be able to realize that between this positive Na and this H3O negative, clearly we have ionic bonds because they're between ions. Ionic bonds are between things that are positive and negative that stick together because of the opposite charges attract. But inside the cluster, between the carbon, between the H and the C or the O, between nonmetals, we know that nonmetals are forced to share electrons, and we call that covalent. So these are questions that could have popped and said, you know, what kind of bonds exist between this salt, this ionic compound? And if you've got a polyatomic ion, by recognizing this cluster in table, what the heck is that? E, you know that you both have ionic and covalent, something that's also picked apart. Next one, number 6. Number 6, the atomic mass of magnesium is the weighted average of the atomic masses of what? Okay, this is weighted average concept. Okay, we have an element magnesium. Okay, well, let's go to the periodic table to take a look at what we have here. So magnesium is an alkaline earth metal right here in group 2. And let's get up close and personal with it. And here we go, magnesium +2. Now, what do we pull out from this? Well, clearly you can see that it has an atomic number of 12, and it has a what? Atomic mass of 24.305. Now, you've been probably taught if you use this, let's say to convert to moles, you'd round that to 24. But what does this 24.305 mean? You should know that this represents an average between all of the existing isotopes using their relative abundances in nature. I'm going to make this up off the top of my head. This is not exactly correct, but let's just pretend that magnesium exists in 2 forms. Magnesium 24. Now, the reason I'm saying magnesium 24 and not saying the 12 is because to be magnesium, you have to be atomic number 12. So that's implied. We don't need that number if you give me magnesium. What makes magnesium special is 12 protons. Now, there are different forms of magnesium. What does that mean? Well, that means that we're still the same magnesium with 12 protons. That's why I have the same symbol. But we're going to be iso. Iso means same. So I'm going to have another magnesium with 12 protons, and only magnesium has 12 protons. So I don't have to write that. But let's pretend that another isotope of magnesium could be 26. Now, what an isotope is, same element, iso means same, okay, but different number of neutrons, okay? 24 minus 12, okay, gives me 12 neutrons. So this isotope of magnesium has 12 neutrons. 26 minus 12 has 14 neutrons. And again, the reason why you can subtract the things that have mass in the atom are the what? The neutrons and the protons. Electrons have mass, but they're so small, they're 2,000 times smaller than a proton or neutron. So we don't consider them. So this different mass numbers are due to different neutrons and protons. But this one, as we just saw, by subtracting the what? The proton number and the neutron number from the proton number, right? This top number is protons and neutrons. They have mass. Table O will show you. And you subtract the proton number, obviously the proton numbers will cancel, and you're left with the neutrons. So any case, the reason why we have this number with a decimal place is because we average these two numbers together. And you may say, whoa, wait a minute. When I average 24 and 26, I'm not going to get 24.3. I'll actually get 25, a number right down the middle. And you'd be right. But this is a weighted average, meaning that we consider the relative abundances of each of the isotopes that exist in nature. Case in point, let's pretend that 80% of all the isotopes in nature are magnesium-24. And then only 20% of all the magnesiums found in nature are magnesium-26. So if 80% is correct, then the average is going to be closer to the 24, and that's how it works. So when we do a weighted average problem, which is part of the curriculum, okay, you take 80% of 24 and add it to 20% of 26, and you'd get these numbers. So these percentages are the relative abundances of nature that we have figured out. So when you averaged or you rounded off to use these problems in other parts of your course, what you were doing was taking the most abundant isotope, magnesium 24, okay, which is another type of Regents question. Like potassium, what's the most abundant isotope of potassium? 39. All you do is round off. If it's closer to 39, that must mean that there's a larger percentage of that isotope that exists. Beautiful. Let's go back to the test. So the weighted average considers the percentages that they exist in nature. So these are all of the artificially produced? No, it's always natural produced. Okay, we can't really keep track of the percentages of artificially produced. It's the natural ones. No matter where I find magnesium in the earth, okay, we take that percentage. So the two most abundant, no, we consider all of them, okay? So all the natural occurring isotopes of magnesium. And sometimes I'll say relative abundances in nature. That's considering the averages. So 6, the best questions. Why would I just take 2 most abundant? It's always about the percentage of all of them. Okay, and we use a mass spectrometer. We see that data be fully supporting this. So 6 is 2. Number 7. Which element has atoms that can form halide? Halide. Halide is a fancy word, pinky up, that represents elements that are in the halogen family. So the halogens are our most reactive nonmetal, and that's group 17. Let's go see the halogens. So what they're saying is which element has atoms that can form halide. What they're saying is which one is a halogen. Now, a halide ion would be a halogen that has a charge. So you've got iodine, silver, strontium, and xenon. Let's go to the periodic table. So our 4 elements are strontium, which you should know is an alkaline earth metal in the same family because of the same number of valence electrons, 2. We have silver, okay, which is a transitional metal. We have iodine, there's our group 17, that's your halogens, and of course we have what? We have our xenon, okay, which is part of the noble gas family. So the only choice there that can make halide ions have a charge is due to essentially the only one that's a halogen. Okay, I try to make it simpler, but I can't. So they're just basically asking you which one is a halogen and not so many words, and of course, just your iodine. So iodine, of course, is the only one who's a halogen here. So 7 is choice 1. Number 8, 2 forms of solid carbon, diamond and graphite, differ in their physical properties due to differences in their, okay. A common theme, we're dealing with carbon-based compounds tend to be organic, and this is definitely the key in organic chemistry. As I'll say over and over again, structure is king, okay? You can have the same type of atoms. You can have the same number and ratio of other atoms bonded, but if you change the structure, okay, you will change the properties. So the physical structure, the type of arrangement of atoms in a crystal will change its properties. So structure is king. I guess I should close my quotes here. All right, so structure is king. It's important you get this. So it's about, okay, their crystal structures. Now you being held accountable for what graphite and diamond look like? No. But you should know that these are both forms, something called allotropes. Allotropes are the same element but different properties due to different structures. As we see in organic chemistry, we have something called here's that word again, isomers. Now, isotope means same element. Isomer means the same chemical formula but different structure. Okay, so again, if we're made of the same things as isomers are in chemical formulas, you have to have a different structure. That's a big key, and hopefully you understand that that does come up plenty. All right. Number 9. Number 9. Which quantity can be calculated for a solid compound given only the formula of the compound and the periodic table of the elements? So what they're saying here is that all I have is a formula. Let's say I have, NaCl, and the periodic table, which gives me what? Well, it gives me the atomic number for each element, and it gives me the mass of each element. Okay, so from that, can I get the density? Now, the density would be a no. Now, they said for a solid compound. Now, for a gas, you could get the density if you're dealing with a gas of or density of a gas at STP. At STP, the volume you'd use is 22.4 liters, since you're going to pick a mole, and you could use the formula mass, or the gram formula mass, by adding up. So you definitely can figure that out. But this is not a gas, this is a solid, so we can't do that. Heat of fusion, you need some thermodynamic data to do that, maybe Hess's law. Melting point, calculating the melting points, well, calculating temperatures would probably be in the realm of something called Gibbs free energy, something we haven't learned, so you can't calculate a melting point in this course. But getting the percent composition by mass, all you need is the mass of each element per mole, which is the atomic mass, and the formula. So if it was NaCl, okay, if I knew the formula was NaCl and I wanted the percent by mass of sodium, what I would do is find the mass of my total, because a percent is a part over total, times 100. And then it comes up in a couple of different points in this curriculum. But in any case, I would have the atomic mass of sodium, which is 23. We'd round that off. And chlorine, 35.4. You can run it to 35 or 34, doesn't matter. And I typically use 35. And you would add these together because there's one of each, and that'd be a 58. Okay, and then of course you would do the sodium's mass. Since I said my example, what's the percent by mass of sodium? And you use 23. And it would times it by 100, and you would get a percent by mass. So all I need is the formula, because the formula tells me the ratio of how many of these atoms. And of course, I need these atomic masses, which if you're not sure, let's go to the periodic table. And there we are, sodium chloride. You would see it's 22.9. That mass number above is what we call the atomic mass, and we can use that per mole of the substance. Okay, so that atomic mass is that number above. Okay, and for sodium it's 22.2, and if we get up close and personal, we can see that the sodium, okay, is 22.9, and that's 23 when you use the mass number. And then of course the chlorine is that 35.4. We can round up to 35. And then just adding them together, because the mass number, although it's protons and neutrons, it also is the mass per 1 mole. And that percent by mass problems are always per 1 mole, because that's what you're going to assume, and you can do that with a percent problem. Any case, so all you need is the mass number and the ratio. So you need the periodic table for the mass numbers, and you need how many of the chlorines and sodiums in the formula. So clearly the answer here is choice 4. Okay. Number 9 is choice 4. Number 10. Which terms identify types of chemical reactions? Okay. Decomposition is a reaction where you have things breaking down. Like water can be decomposed. 2 water molecules can break down, or at least water can break down, into hydrogen gas and oxygen. So that'd be decomposition. The reverse is called synthesis. So decomposition and synthesis are reactions. Now, sublimation and deposition are phase changes. And you should know that sublimation is when you go from, let's say, a solid directly into a gas. And hopefully a teacher showed you that dry ice loves to do this because it has high vapor pressure and weak intermolecular forces of attraction. and it goes to CO2 gas. It skips the liquid phase. And in more advanced class, you'd learn about the phase diagrams and that this is below the triple point. But, so sublimation is a solid directly going into a gas. Deposition is the opposite, and that is a gas like H2O gas going back into, let's say, H2O solid. So it's the opposite of sublimation. And a great example of deposition would be snowing. Water vapor, okay, in the air under the conditions of temperature and pressure causes the water vapor to go directly into a solid. And that's why snowflakes are nice and airy and fluffy, because, hey, there's a lot of space in between them as they crystallize. And freezing rain doesn't look anything like snow, because that's just, solid ice formed from a very dense phase of the liquid as it falls through the atmosphere. Any case, deposition is the opposite of sublimation. These are phase changes. These are not chemical changes. And you should know chemical changes are when the formulas change. These are all phase changes. So the answer that are just chemical reactions is deposition and synthesis. Decomposition and synthesis is the only choice that has just, chemical reactions choice 2. Number 11, the greatest amount of energy released per gram of reactants occurred during a what? Well, you probably finished off in nuclear chemistry, and you probably should know that there are huge amounts of energy changes when it comes to the stability of a nucleus. Okay, now the nucleus has something called a strong force. Not really part of the course, but this strong force is what you're messing with. The ability to keep protons next to protons in a nucleus, these are neutrons that kind of buffer that, is the strong force. So the stability of the nucleus and how it changed to get stable has a heck of a lot higher swings of energy changes as we go from an unstable radioactive nucleus to a stable one by, let's say, the emission of energy or a particle. More importantly, when we split an atom, which is fusion, we're taking an unstable, huge nuclei, let's say uranium, and we're splitting it into smaller fragments, let's say krypton or barium, okay, whatever adds up to all the mass, and some more neutrons, okay. This is not the exact reaction, but what you're doing is taking an unstable, high energy nucleus and making it into a lower energy nucleus. And because we're messing around with the strongest force in nature, we're going to have the greatest amount of energy released as we get stable. These other reactions, okay, redox, substitution, and neutralization, are either about ions or about electrons. So these are about electrons, this is about electrons, and this is about ions, positive and negative. So the stability of these reactions have nothing to do with the nucleus. The change of the nucleus is always going to have the greatest amount of energy. In nuclear chemistry, these are the nuclear reactions always give off the greatest amount of energy, and the rest of the reactions really deal with electrons normally, and they have stability issues as well, but nowhere near the changes that you deal with in the nucleus. So nuclear chemistry, fission, fusion offer great amounts of energy. The bombs dropped in World War II in Hiroshima and Nagasaki were fission bombs, and those two bombs dropped supposedly had the same amount of energy as all the bombs dropped in World War II, to give you an idea. And the other bombs dropped in World War II were essentially redox reactions or electron transitioning reactions. Okay, so in any case, 2 is the answer. You need to understand that nuclear chemistry, changes in the nucleus in energy levels far outweigh changes in chemical reactions with electrons. Okay, choice 2 is the answer for number 11. Number 12. Let's go there. Well, that was weird. Number 12. Which element has atoms with the strongest attraction for electrons? My friends in chemistry, the strongest attraction for electrons is a fancy word for electronegativity. Get this word down. Electronegativity. Negativity. It's a fancy word, so pinky up. And it deals with the strongest electrons. It deals with how well the atom, the nuclei of an atom, can attract other people's electrons. Now, if you notice the choices they gave you, nitrogen, chlorine, fluorine, and oxygen are in a very, very unique position on the periodic table. So let's go there. So here we are in the non-metal section of the periodic table above the staircase where the smaller atoms are. The atoms that are smaller, okay, obviously as we go across the periodic table and up and above the staircase, you get smaller because you have a greater number of protons or nuclear charge in your atoms, so you draw in the electrons. You draw in your own and you're able to attract others. So the most electronegative atoms are in this corner. Notice we're not including the noble gases. They are actually smaller because they actually have more protons, I should say, compared to their other elements in their row or their electron shell. But because of the fact that they are stable in the sense that they already have their filled shells, they don't attract other people's electrons. They have no ability to bond, so we can't measure that ability. Any case, the fact of the matter is, the most electronegative of all elements is fluorine. And that's why the answer is there. It is the smallest of these four. You should know that going across you get smaller, and going down you get bigger. So to answer this question, I can just know that my trends in the periodic table, as I go across, the proton number goes from 5 to 6 to 7. We call this the charge of the nucleus. The nuclear charge increases. So the ability of fluorine to draw in its own electrons and be able to attract others in a bond steadily increases to a maximum at fluorine. Now chlorine's pretty good too, but it's a little bit bigger than fluorine because as you go down, you have an extra shell of electrons. You should know as you go down, it's 2-7, 2-8-7. So you're adding an extra layer of electrons, which means you have an extra shell, which means that your N number, your quantum number, or the size of the atomic radius has to increase because of that extra shell. Okay? And you can also introduce the idea of shielding as well. Now, if you don't like this, you can go to Table S to read electronegativities as well. And here we are with Table S. In Table S, most underutilized table that people forget the information given to you. First, ionization energy, the amount of energy it takes to pull an electron away. Electronegativity is what I'm after, the ability to attract other people's electrons. Melting point, boiling point, density, and also atomic radius is also given. So all this information is given here as well as the symbol in the name. So if we look at the four choices, if I don't like using the trends of the periodic table in terms of size, I can see that my electronegativity value, which is the middle value for fluorine, is clearly going to be higher than the other three. So if you notice, fluorine is above oxygen, nitrogen, and chlorine, as we suspected using our trends of the periodic table, which are as you get smaller, you tend to attract your own electrons more because the protons have a greater attraction or nuclear attraction to pull on electrons. So the answer here is clearly going to be fluorine. It's the most electronegative atom. And maybe you already knew that and didn't need this explanation, but number 12 is 3. Fluorine is the most electronegative. So number 13. Compared to the physical and chemical properties of NO2, N2O has, well, the first thing I realize is that I have a different chemical formula. Compounds differ because of the different ratios. Now, both of these compounds are made up of nitrogen and oxygen, so there is definitely some similarities between them. But the ratio of atoms from one to the other will change the properties. So these are different compounds, different chemical formulas, different ratio. This is a 1-2. This is a 2-1. So these different ratios will give different properties. And they're going to have different physical properties, meaning a different melting point, different boiling point, maybe different hardness, okay? And also different chemical properties. They'll react differently because of their probably different structures, okay? because of their different arrangements and different number of atoms involved. So they're going to have different physical properties and different chemical properties. Anytime you have a new compound, every compound is denoted by a unique chemical formula, by a unique ratio of atoms. And when you change that ratio, you have a different formula, a different compound, and you're going to have different physical and different chemical properties. Very important. 13 is 1. Definition of a compound, you have a unique chemical formula, which gives you a unique set of chemical and physical properties because of those different ratios of atoms involved. Number 14. Which phrase describes a molecule of CH4 in terms of molecular polarity and distribution of charge? Okay, let's make some area for ourselves here. Now, CH4, as we probably remember, is methane from our organic unit. Meth is 1 carbon. If you didn't know that, you'd go to table P. But we're not after that, we're after the polarity. So my friends in chemistry, CH4, if you remember, is a carbon. You have 4 H's surrounding it. And the Lewis dot diagram would look something like this. Look something exactly like this. Okay, don't want to sell myself short at this height. Okay, any case, so I know that this molecule, they're talking about molecular polarity. That means the polarity of the molecule. Do not confuse this with bond polarity. This is the polarity of a molecule. Now, for a molecule to be polar, what it means is we have some arrangement of atoms. I'm just going to draw this kind of flattened circle as a molecule. To be polar would mean that you have really one side is different than another. So that could mean there's an unequal distribution of electrons. Being a negative side would mean you have an unequal distribution of electrons that favors this side, meaning there's more electrons that are on this side that are on the other side. The side that has less electrons, less negative charge, we call positive. So to be a polar molecule, you have to have unequal distribution of electrons. Okay? And that is due to something called a polar bond. Polar bonds are 2 different nonmetals that have 2 different electronegativities that share unequally and create this unequal distribution. As in number 13 or 12, we talked about electronegativity. The one with the higher electronegativity pulls the what? The electrons over to one side. So polar bonds, should be an arrow, polar bonds are 2 or more different atoms creating this unequal distribution. So my friends in chemistry, H and C are 2 different nonmetals. They're sharing unequally because there is a difference in electronegativity. For those taking a higher level course, I know that H and C are very close to each other and considered to be something other than polar, and we'll leave that alone for another course. So we're going to use this course as 2 different atoms, polar bond. So my friends, these are 4 polar bonds. There is 4 unequal distribution of electrons, sorry for that red dot, surrounding the C. So this is a chance to be polar because it has polar bonds. To be a polar molecule, you have to have polar bonds. You have to have an opportunity of sharing electrons unequally. Okay? So this has polar bonds. 2 different nonmetals have 2 different electronegativities, and the one that's more electronegative pulls that pair closer to that side and creates an unequal distribution. Now, to be a polar molecule, the second thing is you have to be asymmetrical. Asymmetrical. Now, why? If you're asymmetrical, that means you're not the same all the way around. Now, look at this example. CH4 is very symmetrical. Yes, it has polar bonds, so the first requirement has been met, but the second requirement has not been met because it is symmetrical. It's the same all the way around, which means what? Even though it's sharing unequally, it's sharing unequally in all directions. So therefore, there's no different side. It is nonpolar. So the distribution of charge, we would say that the molecular polarity is nonpolar because of a symmetrical distribution of charge. Being nonpolar means that my polar bonds or my dipole moments, if you learn them, canceled out because I'm the same all the way around. I may be unequal sharing, but I'm unequal, okay, or I'm equal in my unequalness in all directions, if that makes any sense. Bottom line, if you're symmetrical, you cannot be a polar molecule. And what symmetrical means is that there's a equal distribution of electrons around this entire atom because of the symmetry. So 14 is 4. Okay, number 15. Which sample of copper has atoms with the lowest average kinetic energy? In this course, we're going to use lowest average kinetic energy, and that's tied to temperature. As you increase the temperature, it's a measure of an average motion or distribution of motion. So you're going to need to understand that temperature is directly proportional to the average kinetic energy. Some people say average kinetic energy is temperature, but we're basically going to say that temperature is directly proportional with kinetic energy of the average. So lower the average kinetic energy, lower the temperature. Now, since temperature is an average, I could care less with how much of a sample I have. So since we're looking for the average is independent of how much you have. I can cross off the size of the sample. Just like if I have two classes and one has a higher average than the other, that's independent of how many kids are in a classroom. Average does not matter with the size of the class. Average is just what the average is. It could be 2 students that you averaged, or it could be 30 students. If I was looking for total points in a class, I could add up everyone's grade on a test or GPA to get total points, and that's a lot like what this is, Q equals MC change in T. If I wanted a total number of points or energy, I would use the thermal equation that you have in table T, and I would equal to the mass. We would consider the mass of it along with the specific heat and change in temperature. But here, the average is just the temperature. Okay, in this case, the lowest temperature, since we want the lowest. So who's got the lowest average? Who's got the lowest temperature? Choice 4. Careful when you read this. It's easy to put the highest to the lowest. They were looking for the lowest what? Lowest temperature, okay, is the lowest average kinetic energy. Okay, so number 15 is 4. Number 16. Which change results in the formation of different substances? If we are making different substances, you should know that a substance, okay, represents an element or a compound. Now, an element is just the same group of atoms. It could be diatomic, or it could be the standalone like gold. Compound is a ratio, specific ratio of 2 or more different atoms, as you've learned, like H2O is hydrogen and oxygen in a 2-to-1 ratio of hydrogen to oxygen. Now, to make different substances, which by the way are all homogeneous, you would need a chemical change. So the only one there that's making a chemical change is the burning of propane. You're taking away propane and you're making CO2 and water. You should know clearly that melting, deposition, solidification, all of these guys in 2, 3, and 4 represent physical changes. You're not changing the chemical formula, you're just changing the phase. A solid going to a liquid, NaCl-wise, doesn't change the formula. It just changes the phase or the distance between them, the physical distance. Oops, that should be solid. So that should be clear. And they're asking this question, do you know the difference between a physical change and a chemical change? And clearly, melting, deposition, which again is going from a gas going directly to a solid, as I talked about in another question, is a phase change. Solidification is the freezing of water. You're not changing the chemical formulas when you make them into a solid, liquid, or gas. But burning of propane is clearly a chemical change. They call this combustion, and it's outlined in Table I as well. You should know in Table I, the first, third of all these reactions are combustion reactions. Or you can say they're redox reactions because you see the standalone zeros here. If you see a standalone element, you know immediately it must be a redox reaction because it's a 0 on one side and not a 0 on another. But here, clearly, I have my propane reacting with oxygen to make CO2 and water. This is burning. This is combustion. Anytime you take oxygen in the presence of some kind of organic fuel, this is natural gas, propane, this is gasoline, this is alcohols and sugar, this is like respiration in our body, we use sugars. Energy is released exothermically. This is all examples of chemical changes because guess what? The formulas are changing. Number 17, which substance cannot be broken down by a chemical change? So now, chemical changes, as we've been talking about in previous questions, represent the fact that we are making a new substance by creating a new chemical formula. We just looked at propane in number 16, and it was changing with the reaction of oxygen into CO2 and water. New formulas are being named. Now, you're saying cannot be broken down by chemical change. Now, chemical changes mean that bonds are broken and usually new bonds are formed sometimes. But it's all about at least bonds are broken. If we look at ammonia, we should be aware at this point ammonia is NH3. And if you're not sure that ammonia is, you are being held accountable in this course to know that ammonia is NH3. If you don't know where that is, I'll show you where you can actually look up ammonia. So here is ammonia and aqueous ammonia right here. So if you forget that that compound is NH3, table L shows it as one of common bases that you'll see in this course. So aqueous ammonia is NH3, and as I talked about, there are two different capitals. So there's a bond or three bonds, and therefore you could break this into its individual elements. So we can cross off choice 1 because that can be broken down. There are bonds to be broken because there's two different. Ethanol. Okay, you may say, "Ooh, I don't know about ethanol." But ethanol, okay, is an organic compound. And if you remember, the eth means two carbons, all right, involved. Ethane means there's single bonds between them. And the OL ending means you have an OH group attached, and you fill in the rest with H's. There's clearly some bonds here because we have more than what? One type of atom involved. So there are bonds to be broken here. And if you weren't sure about ethanol, okay, you can look at table P, F, Q, and R to build up what ethanol is like I just did. Okay? Propanol for the same reasonings. Prop is three carbons. Propane from table Q is single bonds. Al means you have an aldehyde ending at table R, which is a what? Double bond to an O and an 8, sometimes a CHO ending. Bottom line here is you can clearly see from the organic part of your course, this has many bonds that can be broken, so it can be. Zirconium, if you're not aware, is an element. It has no bonds to be broken. It's already a standalone element, and you can see that in table S, lists all of the elements. So clearly, choice 2 and choice 3, your organic unit would have helped you realize that these definitely are not elements. Ammonia you may have forgotten if you haven't seen it enough in your class, okay, in that base table that I showed you. Zirconium, if you weren't sure, don't forget table S. Zirconium is an element on the periodic table, Zr, and if again you weren't aware, we can go to table S. Table S is again the most underutilized and unrespected reference table. Not only does it have all these other things listed, it has the symbol and the name. So these are all elements. As we mosey down, we see zirconium is atomic number 40, Zr. It's an element. Okay, these are all elements, and they mean they're the same type of atoms, and you can't break down an element into anything more simpler than that. Same type of atoms. So that's your answer. Choice 4 for number 17, the only element which cannot be broken down. It's the simplest form of matter. Okay, number 18. According to table I, and so they're pointing us somewhere, which equation represents a change resulting in the greatest quantity of energy released? Okay, well, table I is that thermodynamic table, and if we're releasing energy, that should scream to you exothermic, like heat is exiting, okay, exothermic. And you should know if something is releasing energy and is of course exothermic, the potential energy curve, okay, starts out high and comes down because the reactants have a large amount of potential energy and the products will have a lowered amount. And the difference of where I start and where I finish is delta H. And because I'm going down, delta H is negative. Okay? So delta H is negative. So there's, by them saying the greatest amount of energy released, obviously energy has to be released as I go from high to low, I'm looking for the largest negative number. Okay? Since I don't see any delta H's given to me, I'm going to have to look at these four reactions up on the periodic table, on table I, and see which one has the greatest negative delta H. So let's go to table I. So we go to table I and we look for our reactions, and all of our reactions represent synthesis reactions, and we can see that that the delta H's are given to you on the right hand side, and if you forget that exothermic is a negative delta H to show that the energy is dropping because you did release, on the bottom of table I they tell you a minus sign indicates an exothermic reaction. So what I'm looking for in my four reactions, and I have them labeled here in yellow, at least the products of those four reactions, I'm looking for the choice that has the what? The greatest negative delta H. Now if you look at your reactions that are given to you in your question, they don't do it per 1 mole, so they're doing it exactly as written. So of my four choices, NO is positive 182.6 and H3 is negative 91.8 for two of them as written. C2H6 is negative 84.0 and C2H4 is 0.52.4. So as the reactions are written, okay, we would say that this reaction, okay, the reaction of N2 and 3H2, sometimes called the Haber process, okay, is of course the one that is the most negative, which means the greatest amount of energy released, okay, and the most exothermic. So let's go back to the question. So again, the making of the NH3 from N2 was the most negative or most exothermic, and that's why 18 is 3. Okay, number 19 at some point. Which element is a liquid at STP? All right. Now, you can attack this from a couple of different ways. Some people have their students memorize parts of the periodic table that are the liquids. Okay, so let's go there and see who are my liquids from memorization. All right, so we should know who our solid liquids and gases are. And as I would teach my kids, I would say if you take an L, all right, a backwards L, so putting an L on your head if you're that kind of a person, and you put it in front of you and then point it counterclockwise, all right, so it's kind of a backwards L's falling down. Here's one side of the L here, and here's coming down. These are your gases. And there's a little L called Nafkal, so these are all gases. So it's I call it the backwards LL rule. Again, if you put a loser L on your forehead, it's already backwards, perfect for people to see. Point it, I guess, 90 degrees counterclockwise and lay it down. You got two L's, H to the HE all the way to the RN, E to the ISO, whatever that means. NOFCL, the other L, are my two L's there. Okay, so that's all your gases. And then you're going to have two liquids. Bromide's a liquid and mercury. Everyone else is a solid. So this is a non-metallic liquid at STP, and this is a solid. All right. Now, if you still don't like that, when you need another piece of information that could have helped you, you can guess it. Table, the most unrated table, table S could be your friend too. So table S, with all the wealth of information it gives you melting point. So let's go find our friend bromide, and the melting point is 266. Now, how does that tell me it's a liquid? Well, you should know these are Kelvin temperatures, and you should know that 273 Kelvin is equal to 0 degrees Celsius. Now, room temperature, okay, is above 0, but they said at STP. So at 0 degrees Celsius or 273 Kelvin, Well, this is 266. Now, what does that mean? Well, if the melting point is 266 and the air temperature is 273, anytime the air temperature is above the melting point, guess what? It melts. So that tells you because 266 is under 273, bromide is a liquid. So another place to get information by the unheralded, okay, table S. So bromine, okay, is their non-metallic liquid, and choice 1 is the answer. Number 20. Which statement describes a reversible reaction at equilibrium? All right. There are two things you need to understand when you hear equilibrium. And the two keys you need to remember is if I'm at equilibrium, the best way to explain it is if I have 3 people, students on this line, and I have 11 students on this line, and I make the number 1 student from each line switch lines every minute, if I come back in 10 minutes, there have been 10 exchanges. But the actual number of people in each line stayed what? Stayed constant. So the first thing you have to realize is that the amount of reactants and products stay constant. And that is what? Because the rate of the forward equals the rate of the reverse. The amount of people being exchanged were equal. As fast as a person walked to this side, one person walked back. So rate of the forward equals rate of the reverse, and the amount of people in the line stayed constant. Yes, people were changing positions, and the people were changing, the amount was not. So the best answer is either the reactants and products are constant. Never pick the reactants and the products are equal in concentration. That never happens, almost never happens. Remember the tank demonstration. If your teacher did a tank demonstration with water, equilibrium was not matched when the water lines were equal. The equilibrium was attained when the levels stayed constant. If you didn't do that demonstration, sorry, but that's an example. So you're looking for the rate of the forward equals the rate of the reverse. The activation energy of the forward cannot equal the activation energy of the reverse. If that was the case, it wouldn't be a chemical reaction. You would have something like this, a potential energy curve which doesn't exist. Okay? And the potential of the reactants must be equal to the potential of the products. Again, that would be a scenario where you've got a potential energy curve that looks like this, being equal on both sides, and that wouldn't be a chemical reaction as well. So silly choices here. All right? Number 2 is the answer, but don't forget, they love to talk about the idea that the reactants, the amount of reactants and products never equal, but stay constant because the rate of the forward equals the rate of the reverse. Very important one. This pops up a lot. 20 is 2. All right, number 21. Given the balanced equation representing a reaction, what occurs during this reaction? Well, O2 implies we have this idea of O bonding with its 6 valence electrons, double bonding with another O with its 6 valence electrons, making a double bond to occur so that what? Each oxygen is sharing 8 to fill its valence shell. So in order to go from this to oxygen, which we can write as 6 valence electrons, you have to break the bond. Bonds are being broken. You have to get that. Here's a bond between the O's. Here they're free. So you have to break a bond. So bonds are broken. Okay, so clearly 1 and 3 are my choices. 2 and 4 I am getting rid of. Okay, now what's happening? Energy is absorbed or is it released? And this is so vital to the understanding of bonding. Why do atoms bond? Why does O2 exist in this structure? Okay, if you look at the very simple electron configuration, oxygen is 2-6. It wants to have 2-8. It wants to fill those 2 electron spots, 2 more orbitals, okay, need to be filled to make it as stable as it can be. Filling an energy level, okay, gives it stability, the driving force. It wants to become stable. So somehow it needs to share a pair of electrons to make that happen. But the bottom line is bonding is a stable state. The reason atoms become bonded is they use each other to get stable, each one of these. When they're free atoms, they're unstable. So you should understand, if I'm going from a stable state to an unstable state, what do you need? Draw a what? Potential energy diagram if you need to see it. But this is always the case, and this is a big, very big and important concept. Now you need to understand, if I'm going from from a stable state, I have low potential energy. Stable means you have low energy because you don't have the energy to change. Stable means you don't change. If I lay down on the floor in your classroom, you'd say that's weird. You may think that I'm unstable, but I'm actually stable because I don't have energy to change. If you need to make me change, you've got to give me energy or to move. Now, if I'm going to make something unstable, like the free atoms, I'm going to have to go up in energy, and the potential energy of my products is higher. So clearly, to go up, energy had to be absorbed to go from a low state to a high state. My delta H is positive. This is an endothermic process. Okay? So anytime you break a bond, you need energy because you're taking something that's stable to unstable. If you don't like that, anytime you go out to break stuff, and you should never do that, but when you want to go break something, you need energy. Okay? And it's a concept that keeps reappearing. To break a bond, you need energy. We call these bond energies. Now, the opposite is also true. To form a bond, you're creating a stable state, which means the reverse of this, it'd be exothermic. Energy is always released when you form a low energy system. How do you get low? You have to release it. How do you get high? You have to absorb it. Okay? So clearly we're going from stable to unstable. Stable is low energy. Unstable means, man, that high energy is going to do something, and go from low energy to high, you have to absorb. So clearly energy is absorbed as you need the energy to break this low energy scenario up into unstable high energy atoms. Anytime you break a bond, energy is absorbed. So number 21 is 1. All right, number 22. In terms of entropy and energy, systems in nature tend to undergo changes toward what? Okay. Entropy is something you should have learned, and it's the measure of chaos or disorder. And you should have remembered that in nature or the universe's entropy is always increasing if this process is spontaneous. Meaning, if you see a reaction happening, if you see a phase change happening, it's doing so because the overall entropy of the universe is increasing. So one of the driving forces is that we always move toward disorder. And that kind of makes sense because if you're always moving toward disorder and you can ride that energy change toward disorder, we call that free energy. Meaning, when you burn a piece of paper, you clearly see that the carbon is disappearing into CO2 gas. It's disappearing and heat is going on, and the process works. And we're increasing the number of gas molecules, and solid is becoming a gas, so the disorder is increasing. But more importantly, think about nature in general. Does your yard stay clean without you putting energy in? Does your room stay clean? No, we have to fight the universe's disorder constantly because we love order. Okay, biological systems try to make ordered structures from disorder, and it takes energy. That's why living things, especially us, are consumers of energy, because we need the energy to fight the universe. Okay, so clearly we always go toward disorder. If we never cleaned up, the universe would make a very big mess naturally. So we always go toward higher disorder. Big rocks become small little pieces. Okay, things break down in nature naturally. Now the question is, do we go toward high energy or lower energy? Well, that part is about the enthalpy or the delta H. Now, believe it or not, most reactions are negative delta H's or exothermic. Most reactions, okay, start high with energy and go down. Well, because if you have high energy, that means at some point you're probably going to give it off to make your products. Things that can burn, that can give off heat, that can explode eventually at some point do give off their energy to get stable. In nature, a rock on top of the hill eventually usually finds its way on the bottom of the mountain. Okay, so we go toward lower energy. And this is a question that often repeats through many tests. Okay, but we go from higher disorder, which is higher entropy. Entropy is a measure disorder. And we go towards systems where energy is released. If you have high energy, and if you're hyperactive, if you're feeling like you're having a good day, eventually, especially a sugar rush, you crash. Eventually, you give off that energy. Things in nature eventually go down to lower energy. You've had the high energy, well, you're going to do something with it. So we go from higher energy to higher entropy, and then move toward a lower energy by giving off our extra energy. Okay, so exothermic reactions and increasing the disorder is definitely a how the nature tends to move. So 3 is the best answer. Number 23, which term is defined as the difference between the potential energy of the products and the potential energy of the reactants in a chemical reaction? This seems like a straightforward definition, but again, everything in chemistry seems to be tied to a concept. So we go back to our potential energy curve. Potential energy curve. Now, if I had this reaction, it's exothermic. That means I have a lot of energy to start with, and I have a lower amount of energy to end with. And we would say that the reactants have higher potential energy than the products. The first thing you do when you looked at a potential energy curve is see how high this value is and see how high this value. Clearly, the difference of where we start, if I could draw a straight dotted line, and where we finish is delta H. It's the change in heat. So let's pretend that this is 100 and that this value here is, let's say, 20. Okay, well, the potential energy of the products would be 20, right? This is 20. This is the energy of our products minus the potential energy of my reactants, which is 100. And what do we get? Negative 80, and this would be kilojoules. Negative delta H tells me what? Energy went down. So the difference between this value minus this value gives me the what? Heat of reaction. Delta H is another word for enthalpy or heat of reaction. So yeah, it's a definition, but certainly if you understand the concept, you can work it out, as the Beatles would say. Number 24. What is the atomic number of the element whose atom bonds to each other in chains, rings, and networks? Okay. Atomic number of the element whose atoms bond to each other in chains, rings, and networks. Well, chains would mean you have some kind of element that kind of keeps bonding with each other. And one of your units was organic chemistry, where we had carbon chains. In fact, we named the carbon chain. For instance, this has 4 carbons in its molecule, organic chemistry. So this would be meth, eth, prop, bute from table P, and it'd be a butane because of single bonds. So organic chemistry is dealing with the chain bonding or the bonding of the carbon backbone of carbon. All right. Now you say, what about rings? Well, we have monosaccharides, we have cyclo compounds. Some courses might have taught you that if you had carbon bonded to carbon into these rings, this is called cyclohexane. Of course, I'm forgetting the hydrogens, but carbon can bond to itself in rings. It can actually bond to itself in something called a buckyball. But in any case, we're talking about carbon. All right, it's the only thing we've talked about where we have long chain of these carbons into the naming system. So let's go find the atomic number of carbon if I needed to do so. And how convenient. Carbon has atomic number 6. Tells you right there what makes carbon so unique is it's the only atom with 6 protons. That's what the atomic number is. So of course atomic number 6. So the answer is choice 3, atomic number 6. Very careful when you're dealing with numbers and choices if the choices are numerical, and so are your answers. You're looking for number 6, which is choice 3. 24 is 3. Okay, 25. How many pairs of electrons are shared between two adjacent carbon atoms in a saturated hydrocarbon? Saturated is the key here. Saturated means that the hydrocarbon is holding the max amount of H's possible. We have to go to table Q for this. Okay, very, very important concept here. Saturated hydrocarbons are alkanes. Why? Because alkanes have single bonds between the carbons. If they have single bonds, and carbon can only make 4 bonds because it has 4 valence electrons, you can have the max amount of H's. This is C2H6. This has 6 hydrogens for 2 carbons. This is C2H4. Notice there's less hydrogens because of an increase or a higher number of bonds between the carbons. By increasing the bond, you lose 2 H's. This is C2H2. By adding another bond, in this case a triple bond, you lose 2 more H's, and clearly what you have is a 2-carbon system that is unsaturated. These guys right here are unsaturated because they could hold more hydrogens if you were to open up this double into a single, or open this triple into a double or single. These guys do not hold on to the maximum. And again, the reasoning is very simple. Carbon must make 4 bonds. If I'm an alkene, which means I am unsaturated because I don't hold the maximum number, it's because carbon must make 4 bonds. And this carbon makes 1, 2, 3, 4. If I only had 1 bond between the carbon, carbon opens up another opportunity to hold on to a hydrogen. So the general formula for alkanes is CnH2n plus 2. If I've got 2 carbons, you double that. That makes 4. You add 2, and notice I get a 6 there. That's the maximum amount of H's I could have for a 2-carbon system. So my friends in chemistry, we're looking for alkanes. All of these guys, C and H2n, lose the plus 2 because you lose the saturation. And this is CnH2n minus 2. Notice we're getting even smaller in our saturating, okay, or saturation, because we're losing more H's. So in 25, how many pairs of electrons are shared between 2 adjacent carbons, I can't speak today, in a saturated hydrocarbon? So if it's saturated, okay, we have 1 bond. 1 bond between the carbons are alkanes. And you should know that 1 bond represents a what? A pair of electrons, okay? So a pair of electrons. Now they wanted a pair. They wanted how many pairs? Careful with the question. So there'd be 1 pair. They could ask for how many electrons are shared, and that would be 2. Careful with that question. They wanted a pair. A pair, of course, is 2. So there's 1 bond. There's 1 pair. Therefore, the answer for 25 is 1. Okay? So number 26. Number 26, given the balanced equation representing a reaction, this is a redox reaction because I see a standalone. Anytime I can pick out some 0 elemental forms, I know it's a redox reaction. As the aluminum loses 12 electrons, the oxygen, well, if this guy is losing electrons, in this case 12 electrons, in order for the reaction to be balanced, you must balance the charge and the mass. So if something is losing electrons, someone has to gain the same amount in order for this to be balanced and work. So it's called conservation of charge and conservation of mass. So it has to gain 12 electrons. Okay, so very important you understand that. So because of conservation of charge and mass, every reaction has to follow that. We don't talk about that usually with other reactions that don't have changes in charge, but in redox especially, and most reactions are redox reactions, we have to make sure that the electrons that are lost have to be gained, because if they're not, that means we're losing some electrons or gaining some electrons along the way, and that can't happen. So it has to be gained the same amount of electrons that are lost. Conservation of charge. So 26 is 2. 27, which compound is an electrolyte? Circle that word, a very important concept. Electrolyte means that you're able to conduct electricity in solution. And this is due to free ions. Anytime you have free ions that are not locked in a crystal lattice in the aqueous or liquid form, the ions are able to conduct electricity in that solution or that liquid. Let's understand how it works. Okay, if I've got a what? A solution, and I've got positives and negatives and positives and negatives. And if I was to drop a negatively charged object or give on this side, okay, what's going to happen in this solution is the positives are going to come running. If they do come running, okay, the negatives would be a little bit repelled, and what you would have in the future, you would have this negatively charged object in this solution, and you would have all the positive ions attracting it and all the negative ions that were repelled on the opposite side. So you can see the negatively charged object made this side of the beaker get negative because the ions were free to what? Free to move. So who gives free ions in solution? You need to know these. Number one, ionic compounds called salts. Soluble salts, metal, nonmetals, will break apart into ions. Two, okay, acids. You should know acids dissociate into protons and conjugate bases, which could have negative charges. So acids give off ions. And also bases. Bases give off ions as well, like a hydroxide. Okay, acids give off that H pluses. Salts break apart into their respective ions. If it's sodium chloride, Na plus and Cl negative. And you should know that salts do not conduct in the solid phase because they have a crystal lattice that locks their ions up in a particular 3D arrangement that does not allow them to move. Only when you liquefy them or dissolve them in water are you able now to conduct electricity. So the question is really about which one is an acid, base, or a salt. Now when you look at your choices, you can see we're dealing with organic compounds, carbon-based molecules. Table P, Q, and R are your friends here. So you're looking for an acid, base, or a salt. Well, we're not going to have any salts. Okay, so clearly we're going to get rid of the salt because they're all nonmetals bonded to nonmetals. These are organic compounds. I don't see any metals or any polyatomic ions here. Bases. Well, you might want to pick a alcohol if it was a base, but it's not given. So there's no bases here. The question is, can you find me an acid? And you should know that the Cu group is an organic acid. And organic acids, like all acids, dissociate into ions. This is going to produce H pluses. And what's remaining is going to be CH3, COO negative, which we'd call the conjugate base. This is an acid. Now, if you weren't sure what was an acid or a base in terms of organic chemistry or in terms of functional groups, we need table R. R, if you're not from New England, table R. Let's go there. So here's table R in all of its glory. And what do we have? We're looking for an acid, base, or salt. None of these are salts. But wait a minute. There she blows. We have an organic acid when you have a C and an O at the end. So there's your functional group. The R is the rest of an organic molecule. And sometimes, as I just showed you, or in the question, they write this ending as COOH. Okay, and these are acid shapes. In fact, these very electronegative oxygens drift this pair of electrons closer to these two O's, and this H can slough off to be H+. Bottom line is you need to be able to identify which of the following has a COOH ending, which is an acid, which is one of the three electrolytes, salts, acids, or bases. So number 3 is your organic acid, and 27 is 3. 28, which statement describes one acid-base theory? Okay, an acid, by general terms, if it's an Arrhenius acid, you give off an H+ into the solution, And of course, the only thing positive in solution would be an H plus. That's not what they're talking about here. They're talking about the other definition, which is called the Bronston-Lowry definition, which you don't have to know by name. And so you think about acids. Acids have these H's to give off. So it makes sense that the acid is an H plus donor. Acids tend to give H pluses to things. Case in point, if I had acid like hydrochloric acid, which is listed in your reference table, and I had water, well, what's going to happen is the acid's going to donate its H plus to the water. Well, the water now has one more H plus than it had before, so now it's H3O plus, and the HCl lost the H plus and now is Cl negative. So this is the acid because it donated, and this must be the base because it accepted. Okay, so an acid is an H plus donator, and a base is an H plus acceptor. And that's a Bronston-Lowry definition of an acid in base. And you should be able to figure out who the acid and base are in these types of reactions. So like say in the reverse, what is H3O plus going in the reverse reaction? Well, H3O plus in the future has one less, so this must have donated an H plus, which is an acid. This one accepts, which has to be a base. Okay, so 28 is 2. Well, if you got number 28 wrong, 29 probably too, because now we're talking about arrhenius acids, or arrhenius, however you want to call about it. Any case, what are these? This is the most simplistic definition. So you say, oh my gosh, I forget this person. Don't worry about it. What do you think is the most simplistic definition of an acid? Acids somehow are involved with what? H pluses going into solution. And arrhenius bases, just for fun, okay, deal with giving off hydroxides. So to be an arrhenius acid, the most simplest definition, you have to have a what? You have to have an H to give off, to increase. So who are arrhenius acids? Well, this one has the H, and they like to write the H in front to help you figure this out. For instance, table K has a list of these acids that are most common in this course. And if you look, what do they all have in common? Yeah, for most of them, they have an H in front. They're screaming, hey, I give off an H. So an arrhenius acid has to have an H that comes off, so they write it there. Okay? And of course, to be an arrhenius base, the most simplistic of all definitions, you would do what? You would show hydroxides given off. So these are arrhenius bases because they have the hydroxide. Notice ammonia, as we talked earlier in this test, does not have a hydroxide to give off, but because it can accept a what? An H plus off of a water, it can form a hydroxide, okay, as a result of the water donating and this accepting. But we're back at the arrhenius definition, so back to the question. So one doesn't make any sense because we have a base there. This is an arrhenius acid. Yes, this is a salt. There's no hydroxide here. This is not an arrhenius base or an acid, okay? So we get rid of that. This is an arrhenius acid, H in front. So choice 4 is your answer. It's the only one that has 2 H's in front, denoting the fact that H pluses come off. And that's the most simplest definition. 29 is 4. Number 30. Which statement describes the stability of a nuclei of potassium atoms? Now, when I'm talking about stability of a nuclei, I automatically think nuclear chemistry. Anytime you're talking about the nucleus, okay, I'm thinking nuclear chemistry. And I know that when the nucleus is unstable and has high energy, it does something to get stable, like give off an alpha particle or a beta particle or a positron or just X-rays, electromagnetic radiation. Now, which statement describes the stability of nuclei of potassium? All potassium atoms have stable nuclei. Well, that's a tough one. Every time you say all or everything, I don't trust it, but I know for a fact that there's a place I can look to test this. There are some selected radioisotopes, isotopes of potassium, that are radioactive, which means they are unstable. If you're radioactive, that means your nucleus wants to change itself to get to a more stable nucleus. So we're going to go to table N, sometimes affectionately called table na. So table N, let's go. So table N gives me a bunch of nuclides that are radioactive, which means these are particular isotopes of certain elements that have a nucleus that needs to change because it has too much energy. And as you learn, that could be because of a incorrect ratio of neutrons to protons, high or low. So the type of decay mode or type of decay can be listed in table O to figure this out. But I just want to know, is there any potassium that's unstable? And look, there are two potassiums, two isotopes of potassium. Iso means same element, same number of protons, different number of neutrons. There are therefore different mass that are unstable. So the ones I see two potassiums that are listed as radioactive elements that undergo some kind of emission from their nucleus to change their nucleus from an unstable high energy nucleus to a stable nucleus. And again, that's due to mostly the ratio of neutrons to protons when it was made. So potassium has examples of isotopes that are unstable in their nuclei based on table N. So all potassium have stable nuclei? No. All potassiums have unstable? No, because I know that the most common isotope of potassium, okay, which we can find in the periodic table, so the most common isotope of K, potassium, that's unstable, is potassium 39. The highest abundance of potassium is always averaged out in this number with a decimal point. So 39.0983 rounds off to 39, so the most common isotope of potassium is K39, which is not what is listed in table N. Table N has K37 and K42, not 39. So that means that all potassium is not radioactive. So we'd say some potassiums have unstable nuclei that spontaneously decay. And that's the best answer. And you would, and now 4 makes no sense. Some potassium have unstable that do not spontaneously decay. Now, if you're unstable, you would give off naturally particles to relieve your stress and relieve your energy requirement. So this doesn't make any sense. Things that are unstable spontaneously, which means they do give off their particles and energy to get stable. So number 3 is the best answer for number 30, choice 3. And this concludes the first part, 1A, or A1 if you want to call it, of the easier of the multiple choice. Now we're going to start part B1, which is part of the harder multiple choice. Sometimes I see it, sometimes I don't. These often have 2 steps to the problems. Again, sometimes I can see that. Number 31, which is the first question of part B1. These are the multiple choice questions that are supposedly a little more challenging, may have multiple steps. Again, we'll see if that's the case. So number 31, let's get up close and personal. All right, so in this question, which notations represent different isotopes of the element sodium? So isotope, important word here, and isotope means, iso means same. So isotope is the same element but different number of neutrons. They have nothing to do with different number of electrons. You should know if you are making something called an ion. All right, you may have learned this to be a cation and this to be an anion, but in any case, when you have charged atoms because you lost or gained electrons, all right, we call these ions. These are not isotopes. Yes, they have the same number of protons, but these have different number of electrons, so we get rid of them. So we want different isotopes of the element sodium. So you're going to need something with a different mass number. So clearly you can see choice 1 is a possibility, or choice 4, because they have different mass numbers. And of course they have different mass numbers because they have different neutrons and protons. Remember, the mass number of an element is the protons and the neutrons. So the proton number will be the same if you have the same chemical symbol, right? And that was denotes, like sodium's, all right, atomic number 11. So that 11 will be down here. They don't write it because the symbol implies 11. So it's either choice 1 or choice 2. So really the question is, do you know that sodium is Na. And if you did not know that sodium was Na, because sulfur is an S, there's a place you can look, and that's table S again. And if you've been following along with me, table S is the most underutilized table. Well, let's go. So table S in all of its glory has all kinds of information there for your viewing pleasures. We're just there to, at least I'm here to show you exactly what they can offer you in terms of the name. So sodium, Na, there's the symbol and there's the name. So if you weren't sure, a good place to look for element symbols and names is table S. Sulfur, okay, is the S. So that's a little trick in that. But you had to know that isotopes were the same element, different number of protons, and that, of course, sodium is Na and natrium is the old, I believe, Egyptian name of the sodium. Any case, moving forward. So the answer is choice 4 for number 31. Isotopes, same element, same number of protons, different number of neutrons, therefore a different mass number, but of course sodium is Na. Okay, number 32. Which electron configuration represents electrons in an atom of gallium in the excited state? Okay, now a couple of things here. They gave you the word atom and they gave you the word excited state. Now, when they say atom, and I always think of a dance party, you say atom, I say neutral, atom, neutral, atom, neutral. All right, so atoms are always neutral. You should always recognize when you hear the word atom, neutral is involved, which means the protons equal the electrons to give you an overall zero charge. We know that standalone atoms in redox, like say zinc, are zero, or something like hydrogen, whether it's bonded to itself, is still a zero in its elemental form. Protons equal the electrons. So the first thing I'm going to do is notice what is the electron configuration of gallium, or how many electrons should it have. Okay, so let's go to the periodic table. So when we find gallium, we find that its electron configuration written below, okay, represents how many electrons can fill each of its 4 shells. It is occupying four different electron shells, and these are, of course, the total number of electrons in each of those 4 shells, 2 being the first and 3 being the 4th shell. Now, of course, atomic number 31 tells me gallium is different from every other atom in the periodic table because it has 31 protons. But they said gallium was an atom, which means neutral, atom, neutral. So gallium has 31 protons, but also has 31 electrons. Okay? So that's important you realize that. So having 31 electrons, okay, is very important. So 2-8-18-3 represents the ground state. This is how the electrons exist in a neutral atom of gallium when everything is in its lowest possible energy state for the electrons. Now, an excited state, as the word implies, means you're not in the lowest grounded state. You're in a state where you have high energy. And you should have learned, in order to go from a low energy state to a high energy state, electrons have to jump away from the nucleus. Think of the nucleus, okay, as right here, okay? And let me just get rid of these electrons here. Let me just get rid of this stuff. I guess that's a worse way to do it. There's a better way, I should say. So let me get rid of that. Now, think of the positive nucleus in front of the 2 and the 8. So these are shells. Think of that as, hey, that's electrons in these shell of electrons. Now, in order to go from, let's say, the electrons to jump from the lowest energy position to higher energy positions with farther away, electrons have to leap away from the what? The nucleus. And if they're leaping away from the positive, they have to overcome its attractive force. So they need energy. So becoming an excited state means you're jumping away from the nucleus because you have the energy to do so. Electrons that are closer to the nucleus don't have the energy, or they're grounded or stable in low energy because they're being affected by how close they are to these protons in the nucleus. So we're looking for something that jumped away from this very stable state that has 31 electrons. Let's go back to the problem. Okay, so returning back to the problem, as you saw, the ground state written in your reference table or your periodic table is 2-8-18-3. This is not an answer. This is the ground state. This is the lowest energy state. So this is not the answer. So we need something that's going out of order. Now, if you look at choice 4, this is also the ground state, but it has one more electron. So if it's an atom, this would not be gallium. This would be germanium, atomic number 32. This has 32 electrons, right? So this would be the ground state of germanium. So 4 cannot be a choice. Now, if we look at choice 1 and 2, we see electrons going out of order. Look at choice 1 for a second, 2-8, 18-3. Now we know that 18 electrons fill the third energy level. But now an electron must have jumped from the third to the fourth in order for this to happen. Notice 2 and 8 are still the correct numbers. 2 electrons fills the first energy level, 8 fills the second, 18 fills the third. So apparently an electron leapt away, I guess, from the positive pulling force of the nucleus and jumped to the fourth. So this is an excited state, but is it gallium? Well, if you check out how many electrons this would be, this is actually not, this would be 30 electrons. So this is not 31 electrons. 8 plus 2 plus 17 plus 3 is 30 electrons. It's got to be 31 electrons. Gallium's atomic number 31. So this is an excited state not of gallium, but of zinc. Zinc is 2-8, okay, 18-2. So you can see an electron jumped from the third to the fourth, jumped away, okay, as it absorbed energy to become excited. So this is the wrong number. So this is excited, but it's not gallium. If you look at choice 2 and you add up these electrons, you'll see that these equal 31, which is exactly the number of electrons that an atom, hey, neutral, of gallium has to have, and it's going out of order. Notice if you put this back in where it's supposed to be, you can't start filling the fourth energy level until you fill the third when it's in the ground state. So this is supposed to be 2-8-18-3. What happened? Well, an electron from the third jumped to the fourth and became excited as it gained energy in order to pull away from the nucleus. So this went down to a 17, this went up to a 4. That's why 2 is the answer. It's going out of order. Sometimes I'll tell my students, if you're looking for an excited state, look for a hole, look for a place where electrons should be. We have 2 of them in 1 and 2, but you had to make sure in this example, you just didn't pick the first excited state you saw, because you have to check if it's an excited state of an element. Gallium is an atom, neutral, which means the protons equal the electron. And gallium, atomic number 31, having positive 31 nuclear charge, would need 31 electrons to be neutral and be an atom. So the electrons have to equal the atomic number. 32 is 2 for those reasons. 33. Which statement describes general trends in electronegativity and first ionization energy as the elements in period 3 are considered in order from Na to Cl? Okay, so we have some things we should know. Electronegativity is that fancy word, pinky up, okay? That means what? Attraction for electrons. So this is a big word. You've got to know what this means. Attraction for electrons and bonds, actually. So attraction of electrons, we'll just keep it like that. Ionization energy is the energy needed to make a positive ion. So it's the energy needed to what? To pull electrons away from atoms. So it's the energy needed to what? Energy needed to pull electrons away. To pull electrons away from atoms, and you would make them positive. All right, now what the heck is period 3? Well, period 3 is row 3. So as we move from sodium to chlorine, we're going across the periodic table from left to right. Now, they want to know what the general trends are. Well, you should be aware that as we go from left to right, the size of the atoms like sodium, okay, as we go from sodium to magnesium, the size of the atoms get smaller as we go across, and you should know why. because the number of protons increases, and we would call that the nuclear charge increases. Okay, so as we go across, the size of the radius gets smaller. Now, not talking about that here, but there's implications, and you should understand this as something that could come up in another part of the test. As you have more protons, or we use the word nuclear charge, right? Nuclear charge is the what? Positive pulling force of the nucleus. Nucleus has protons and neutrons. Neutrons have no charge. So as you add protons going across a period, the amount of attraction that it can have for electrons increases. Electronegativity has to increase. It's the reason why the atoms get smaller. As you add more protons, it pulls in the electrons. So the electronegativity, or the attraction for electrons, has to increase, okay, as you get smaller or go across the period or a row. Now, what happens to the first ionization? How is it related? Well, if you're pulling in these electrons, okay, or attracting them more, doesn't it make sense that when the atoms get smaller because you're attracting electrons more because of more protons, that'll be harder to pull the electrons away. So the smaller the atom, which is small because there are more protons that attract the electrons more, doesn't it make sense that if these electrons are being pulled closer into the nucleus, they're going to be harder to remove? And of course it does. The reason why atoms are smaller, again, is because the high nuclear charge, the high number of protons that these have compared to the ones off to the left, pull the electrons in, which means they attract them more. So higher the attraction of electrons, well, the more energy you need to pull them away. So electronegativity increases, okay, and the first ionization energy both have to increase. So if your attraction for electrons for an atom increases, then it's going to take more energy to pull them away. So that's why 3 is the answer. But I can't say enough, and I keep saying this, and I keep harping on this, and it's kind of weird because I don't have a harp, but I keep harping on the idea that Table S is another place to look. If you weren't sure about the general trends of these two things, you could go to Table S and see so. Let's do that, yeah. So Table S, the most underutilized table, has first ionization, has electronegativity. So if we go find our sodium and go across the period from sodium to, say, chlorine, all right, and again, our sodium is right here. And if we were to go from sodium, we can see that the electronegativity steadily increases as I go from sodium to chlorine. All right? So we can see that 0.9, 1.3, 1.6, 1.9, 2.6, it's all increasing. And of course, what's happening to the first ionization energy? The first ionization energy is right here, and that number is steadily increasing as well. So you don't have to always know the trends. It's very helpful to do so, but you have the time on this test to go to Table S and go see the trends for yourself as we move from sodium to chlorine. For those didn't know that period 3 was going across the row, yeah, that was something you had to know. All right, and of course, going across the row means you are going across the period. And here's the periodic table just to show those that didn't know. Going from across period 3, this is the period. It says period 3, okay, or right on the periodic table, period 1, 2, 3. So in the third period, you can see we're starting from sodium and going to chlorine as we go across, okay? So all of that information is there for your viewing pleasures. So again, whether you knew the trends and understood how this works, or you look at Table S, this is a question you should not get wrong. And information is there in your reference tables, a lot of it when it comes to trends. So obviously number 33 is 3. Okay, moving forward, number 34. What's the gram formula mass of iron nitrate? Okay, well, let's get some room here. Gram formula mass is the mass per 1 mole, okay, of the compound. So the compound is FeNO32, And to find the mass per 1 mole, we're using mole theory, okay? And what we know is that we can go to the periodic table to answer this question. But let's start with writing how many of each of these atoms are in 1 mole of this compound. Now, some people say, oh my gosh, the mole, I'm always getting confused. The mole concept is a very basic understanding of trying to take the understanding that atoms or molecules or chemistry in general are about the number of particles. Okay, so somehow we have to get to the point where, hey, one particle has to collide into another for a reaction to occur, called collision theory. So it's really about the number of particles. So mole concept is understanding of how we get to this point of particles and ratio of particles. So anytime you understand and deal with moles, think about you dealing with a how many number. Dozen represents 12. Mole represents some number of particles, so that we as chemists or students can start thinking in terms of how many of these particles collide with these particles. In the case of a chemical formula, okay, like we have here, in one of these, don't we have one iron atom? And the answer is yes. Now, we can't really deal with one atom in chemistry. It's too tiny. We can't even mass it. It's all theoretical, okay? But we can deal with a mole of them, some number of them. So if I have a mole, who cares what the number is? We know it's an Avogadro's number, but if we have 1 mole of them, okay, in one of these, don't I have one Fe? In a mole of these, I have a mole of Fe, and the answer is yes. In 1 mole of these, don't I have 3 moles of N? So it's really a ratio kind of thing where we're dealing with how many. So there's 3 nitrogens in one of these particles, or there's 3 moles of nitrogen in 1 mole of these particles. Now, the other thing is, how many oxygens do we have here? Well, there's 3 times 3, there's 9 oxygens in one of these. All right, or you can say in 1 mole of these, there's 9 oxygens. Now you may say, how do I get 9? Because a lot of people like to add these. Remember, this is an iron that happens to be +3. And you have how many nitrates surrounding it? Look at the 3 here. There's 3 of them. So if you look at that, there are 3 nitrate ions. Each one is -1. That's involved in this compound. Notice +3 and -1 gives me a 0. So if you can see that there's 3 nitrates, mind the 3 outside the parentheses, you can clearly see by adding up these 3 oxygens in each nitrate ion, you have 9 altogether. So what we're going to do now is go to the periodic table, and we're going to find the mass per 1 mole of iron. Can't do it per a single iron atom. That's why we use mole concept. Again, I'm not going to teach the entire thing here, but in 1 mole of iron nitrate, there is 1 mole of iron. To figure out the mass of 1 mole of iron, we go to the periodic table. So when we find iron, we find that its atomic mass, the mass number, the top number with the decimal point, and of course it has a decimal point because this represents the weighted average of all the isotopes using their relative abundances in nature. But when you look at this, this represents the mass of 1 mole of iron. So if I have a certain number of iron atoms, which is Avogadro's number, this is exactly the mass if I have that many. We made it that way, part of the mole concept. So we're going to round this off to use the most what? Abundant isotope. So 56 would be for 1 mole of iron. So I would go 1 times 56, and that gives me a grand total of 56 for all the irons. Now I have 3 nitrogens, 3 times the atomic mass of nitrogen, and we can see 14.0067 is the relative, I would say the atomic mass, or the relative atomic mass of nitrogen, which is also what? The mass per 1 mole of nitrogen atoms. So we round this to be 14. 3 times 14, and that gives me a grand total of 42. Okay, so I had 3 moles of nitrogen atoms in 1 mole of this. So 3 times 14 is 42. And of course we have, in one of these, we have 9 oxygens. Okay, so 9 times, what's the atomic mass of oxygen? And oxygen has a relative atomic mass of 15.9994. We'll round that to 16 for the most common isotope, or most abundant isotope in nature, which is O16. So it's 9 times 16. If you know your 16 timetables, I believe that's 144. And then I'm just going to add these together. 144 plus 42 plus 56. And I get a gram formula mass to be 242. And of course that represents how many grams per single mole of iron. And of course that is choice 4. So again, how do I remember this problem? You probably remember doing this year, but how do I remember to do that? Well, just think of the word gram formula mass. What is the mass of the formula? Okay, and so you find the mass of each one of these in the periodic table. Who cares if you don't understand mole concept at this point? I kind of do, but you can figure this out by, okay, I need the mass of the formula. I get the masses from the atomic masses of each of the atoms, as long as you know how many of each are in one of these. Okay, so 34 is 4. Number 35, given the balance equation representing this reaction, the mole ratio of the sodium hydroxide, the base, to another base, weaker base, aluminum hydroxide, is what? Well, the mole ratio, and here we go with the mole concept again. All right, the mole ratio represents, again, how many. The mole is about a how many number. It's a concept that keeps track of how many particles we have for many different reasons that are important. One important reason, especially in stoichiometry, is knowing the mole ratio of one compound to another. So sodium hydroxide has a coefficient of 6 in front. That means you need 6 of these for every 2 of these. So there's a 6 to 2 ratio, which we can reduce to lowest terms to 3 to 1. And that's why choice 3 is the answer. Okay, normally in a ratio you reduce, again, 6 to 2. So we're just looking at the we're just looking at the coefficients, and the coefficients tell us how many of these formulas we need for this reaction to work. And it's a 3 to 1 ratio, nothing more. Now be careful with this question. They said sodium hydroxide to aluminum hydroxide. So I had to give the number from the sodium hydroxide first. They could have said aluminum hydroxide to sodium hydroxide, and that'd be a 1 to 3. And that's what choice 2 shows you. So you have to be careful. What are they speaking about? Read this carefully. Sodium hydroxide to aluminum. This one to this one. So that should have been an easy one. If you forgot it, you didn't know that the coefficients tell you how many. Mole concept is about how many. And stoichiometry is about that as well. So in any case, 35 is 3. Number 36, which equation represents a single replacement reaction? Now, if it's a single replacement reaction, we're going to replace one compound with another, okay? So if we let's look at choice 4 for a second. Now, choice 4 is not the answer, but I want to show you something. Choice 4 is made up of H, which is H plus, chlorine, which is -1. It's made of a hydroxide ion. I'm splitting apart the things that are positive and negative. K is +1. Hydroxide from table E, or I call what the heck is that table, is a cluster called a polyatomic ion. That hydroxide is -1. Okay, so what's going to happen is this +1 is going to hook up with the -1 of the other compound. That's what we have here, K plus and -1. And this H plus is going to hook up with this hydroxide to make HOH. Now, water is written this way, but you could have written it as HOH to see that. So 4 represents a double replacement. You have 2 compounds replacing each other, so double replacements. And by the way, 4 is a double replacement. It's also called a neutralization reaction. Neutralization reactions are double replacement reactions. Here's an acid, here's a base, here's a salt, and water. Remember the demonstration? Okay, I had the strong acid, strong base, poured them together, and you drink the salt water. Don't suggest you do that. Now, what else do we have? Well, in choice 1, we have one thing breaking apart into smaller pieces. This is decomposition, or sometimes called analysis. So you can call this analysis because you're analyzing what it's made out of when it breaks down, or decomposition. Now you could also call it A redox reaction, for those that are screaming at me in my class, because you can see that there is a standalone element. If there's a standalone element anywhere in your what? In your reaction, it's a redox. Why? Because it's zero. And if it's zero here, it's something other than zero somewhere else, which means its oxidation number's changed. Okay, just a little aside. Number two, we're the opposite of decomposition. This is called synthesis. Things are coming together to make one thing. So this is called synthesis. And this is somewhere in your test you'll get this. So it's the opposite of decomposition. Also, you can call it what? A redox reaction. Why? Because there's a standalone element. All right? So synthesis. All right, now number three is your answer. And you may say, well, how do I know it's single replacement? Well, because the magnesium's going to replace the H. And double replacement, number four, you had two things double. Here, magnesium replaces the H. The H gets kicked out to be a standalone element. And there is the magnesium with the sulfate now. This is an example of one of the classic examples of a redox. So this is single replacement. Now also, as I just mentioned, because you have two standalone elements, okay, it's also redox. So it's a single replacement, which is a famous example of the redox reaction. So I say redox for those because if they ask what this reaction is in part two, and you forgot it was single replacement or synthesis or decomposition, and you see a what? You see a standalone element, I expect you to say redox, and that would be right. If they said to you, what kind of reaction is this? And you see a standalone, say redox if you forgot what the other ones are. Now in a multiple choice scenario where they're asking for analysis, synthesis, okay, you won't have that opportunity, but you should be aware. The answer is 3, single replacement 36. Now, if you hate the fact that I'm going over all these other things that are involved in the question, I'm sorry, but that's the way that I'm going to do business. Understanding all of the questions and all the concepts behind every question is how you appropriately study for this test. Okay, so 37. The accepted value for the percent by mass of water and hydrogen is 36%. In a laboratory activity, the student determined the percent by mass of water and hydrogen to be 37.8%. What is the percent error for the student's measured value? Okay, so they want you to calculate a percent error. So let's make some room for this. All right, and a percent error, you have almost all the formulas you're going to need in table T. So let's go there. And voila, here is table T in all of its glory. Okay, now density, mole calculations, percent error, that's our hero right now, percent error. So you take the measured value, which is your experimental value that you measured, minus the accepted over the accepted times 100. So that's what we're going to do. So the measured value is what the student did. Student determined the percent by mass to be 37.8. So the measured value from table T, 37.8, okay, minus the accepted value, the known value is 36.0 over the accepted. Remember, it's about something called accuracy of your results here. So it's how close you are to some standard. And of course, you're finding a percentage, so you're timesing it by 100. So you just do that in your calculator. Okay, measured minus accepted, 37.8 minus 36, divide by 36, and you get 0.05 times that by 100, and you get a 5%. Okay, so 5.0%, and of course that is choice 1. So that's a straight plug-in. You probably have done this in many of your labs. Hopefully, if you forgot this wrong, if you got this wrong, you now understand that's one you should not get wrong going forward. 37 is 1. Number 38, the boiling points at standard pressure of 4 compounds are given below are given in the table below. Okay, which type of attraction can be used to explain the unusual high boiling point of water? Now, what this is after, this concept of this question, is understanding that boiling points, which represent the temperature that it takes to have a vapor pressure of the liquid match the atmospheric pressure pushing down on a liquid. You need to understand. Now, of course, that boiling is when the atmospheric pressure of the molecules outside of, let's say, the beaker where the liquid is, pushing down on the surface of the liquid is equal. So now vapor pressure, okay, is due to what? Well, if you have a liquid, actually the liquid should be down here, the surface of the liquid. Liquid molecules, for them to boil, have to overcome their intermolecular attractions, not bonds. They have to overcome their attractive forces. And you learn, if I have strong attractive forces, which most of the time is denoted by dashes, not well, little dots, not dashes, to show that these are not bonds. But if these attractions are significantly or they're strong, it's hard to remove them from each other. It's hard to separate them, and you'll have a higher boiling point. So higher the boiling point, okay, the stronger the intermolecular attractions, okay, or intermolecular forces. Sometimes we'll teach them, I say IMFs. So higher the boiling point is due to the higher attractive forces. And you should have learned that H bonding is the strongest of all the intermolecular attractions. Water is special. Water is very, very light compound. It's 18 grams per mole, yet it has an extremely high boiling point for how light it is. Why? Because water has this unique way of attracting each other. And that's it, attracting. Here's oxygen, who is very electronegative, which means it attracts electrons, okay, and it bonds with two H's. Now, these polar bonds, because of the high electronegativity, the oxygen pulls that pair closer to it and exposes what's left over in hydrogen, which is really just a proton. This is the positive part. So this positive part of the molecule, which is essentially a proton, attracts the what? The negative end of another water molecule. They call it H bonding, but it's just an attractive force. So H bonding is the attractive force between hydrogen, who is bonded to a very electronegative atom that exposes its electron deficiency or proton. So water has a high boiling point, something they love to ask about because of its H bonding. Not its bonds between O and H, but the attractions between the molecules. That's very important. So here's my molecule. It's attracting another molecule. You're not breaking these bonds. You're just attracting the negative end of this water molecule with the positive end of another. And there's your H bonding, the attractive force. Okay, and the reason why H bonding is the strongest is because, again, you have an H who's really, really positive because it's being bonded or is bonded with a very electronegative atom that pulls that pair closer. So this positive end is going to attract something that's very negative, and that makes for a high attractive force, which means you need high temperature or high thermal energy to overcome these attractions to create a vapor pressure that can match the atmospheric pressure. I know I'm giving you a lot here, but these are things you have to know for other questions anyway. But if you want to make this simplified, water undergoes H bonds. It's the reason why it's different for many reasons. So number 2 is the answer, choice 2, number 38. Number 39 states which represents a molecule with the most polar bond. Now, a polar bond has nothing to do with the molecule. We're talking about how well atoms share electrons. These are all covalently bonded compounds. How do I know? Nonmetal and nonmetal. These are all above that staircase on the periodic table. Now, what do we know about these nonmetals? They're all smaller. If they're smaller, they attract their electrons very well. And if one of the two in the bond is more electronegative, it'll pull that pair closer. So we're asking for the most polar bond. What I'm really asking is for the most unequal sharing. Sharing electrons is a covalent bond, and you should know why they occurred in covalent bonds. Why? Because these guys are smaller. If you look at the periodic table, you'll see that these guys are in the smaller area. Over to the right and up represents your nonmetals. They're small. They attract the electrons so much they attract other people's electrons. So these have very high electronegativity. You put them together, they're going to pull and fight for electrons and be forced to share. Now, who is sharing the most unequally? Well, who has the greatest difference in electronegativity? So how do I know that? Well, best probable way to do this is go through your table S again. So we have carbon and oxygen. Let's go find their electronegativity. So at table S, we see that carbon has electronegativity of 2.6 and oxygen has electronegativity of 3.4. So given these electronegativities that we get from table S, carbon is 2.6, oxygen is 3.4, let's just do what? Let's do what? Subtract them. 3.4 minus 2.6. The difference in electronegativity will tell me, okay, who is the most polar. If there's a greater difference in electronegativity, then you're going to have someone winning that war for electrons a lot more and pulling that pair closer. So the 3.4 minus 2.6 gives me a 0.8 difference. Let's go find number 2, where we have nitrogen and oxygen. Well, we know oxygen is 3.4. Let's go find my oxygen in table S. And at table S, we see that nitrogen has also another electronegativity, is 3.0. So 3.0, and we subtract these two, we get an electronegativity difference of 0.4. So you can see in choice 1 and choice 2, the difference in electronegativity is greater so far in number 1. It has a greater difference, which means oxygen, being that much more attractive to electrons in carbon, would pull the pair of electrons or pairs of electrons closer to it, making this side of the bond more polar. That's what this is about. So choice 3, we have H and I. Let's go find H, and let's go find iodine's electronegativity. Back to table S. So hydrogen has 2.2, and yeah. So hydrogen has 2.2 electronegativity, and as we go find iodine, iodine has a 2.7. So 2.2, 2.7, and that would give me a difference when I subtract of a 0.5 electronegativity difference. And then we can go to choice number 4, where we have hydrogen, which you already know is 2.2, and now we have to find the chlorine, and the chlorine is 3.2. So the chlorine being 3.2 that I have right here, we subtract that and we get a difference of 1.0. So the formula that represents a molecule with the most polar bond, which means the most unequal sharing or the greatest difference in electronegativity, is choice 4, hydrochloric acid, HCl. All right. So the greater the difference in electronegativity, the more unequal sharing you have. So if I have HCl, chlorine would pull this pair that it's bonding with closer to it more so than the other because the difference in electronegativity is greater. Chlorine is that much more electronegative than the H, so it pulls that pair closer, and that's where we get the unequal sharing. Okay, number 39 is 4. Number 40. The graph below represents the uniform heating of a substance from the solid to the gas phase. This is a heating curve. You should know that this is the solid phase. This is the liquid phase and the gas phase exclusively. Okay? And where you have a phase change, you should know the temperature stays constant, or the what? The kinetic energy, right? Temperature is proportional to the average kinetic energy. So this would be a solid turning into a liquid. This would be the melting temperature, or freezing if you're going down. And this would be the liquid going to the gas phase, as I like to say. Solid, liquid, more energy. Gas flies around. We'll skip this version. All right. So clearly, you have two phase changes. And the phase changes, if you remember, are the places where the temperature stays constant. Okay. The lower temperature phase change, of course, is going to be your melting. Your higher temperature phase change is going to be your boiling. So the segment that represents boiling, which is a liquid going to a gas, of course, would be D to E. Not sure what else I can talk about. I'm feeling frustrated. There isn't more things for me to talk about here. So in any case, DE is the segment. BC, what other things you could hear from this type of question is which segment or which segments are the average kinetic energy constant, and that would be the two phase changes, BC and DE. You can also get this question, which segments is the kinetic energy being converted into potential, and that would also be BC and DE. Okay, so different ways to look at these questions. 40 is choice 4. 41, a 1 gram sample of a compound is added to 100 grams of water and the resulting mixture is thoroughly stirred. Some of the compound is then separated from the mixture by filtration. All right, based on table F, which is a solubility guidelines table, the compound could be what? Well, the key to the question was, was that the compound is separated. Oops, I wanted something else. The compound is separated from the mixture by filtration. You cannot separate something that is aqueous from a filter paper. A filter paper will not separate, if you have a cone in a filter paper, will not separate ions. So if you've got sodium ions, they're not going to get stuck in the filter paper and the water goes through. That's impossible. The sodium ions, or most ions who are soluble, are interacting with the water. Okay, so as the water goes through, so does the ions. All right, but what you will collect by filtration is anything in the solid phase. In the solid phase, you have a crystal of this compound who is much bigger and will get caught. So we separate things that are not dissolved. If something that's in a solution, something that's aqueous, will go right through the filter paper. Something who is solid will get stuck. Okay, and very important to understand that. So what they're really saying to you, which of the following things are solids, are insoluble? So let's go through the choices. Nickel chloride, table F we go. So the first compound, nickel chloride, is it soluble? Well, I don't see any nickel listed here, but halides, which are from the halogen family, group 17, chlorine's listed, and they're soluble. There are some exceptions, which means if they were bonded with it, they would be insoluble, but nickel chloride is not an exception, so we would say anything with nickel chloride is soluble. Therefore, 4 cannot be a choice that's viable or correct because it's soluble. We want to what? Collect a solid. All right, we want something to be a solid to be collected in my filter paper. All right, so solids get collected, precipitates, not something soluble. How about NaCl? Well, for 2 reasons, NaCl is also soluble. It has a group 1 ion, which is a alkali metal. Anytime you have an alkali metal involved in your compound, that compound is always soluble, no exception, so NaCl is soluble. Also, there's a chlorine involved, and chlorines are also soluble, and Na is not an exception. So for 2 reasons, NaCl is soluble. So we can cross out NaCl. Calcium chloride, well, let's check that out. Now there's no calcium listed here on either side. I mean, there's an exception for sulfates, but what else do we have? Chlorides. Okay, well, chlorine is soluble. Calcium is not an exception, so calcium chloride must be soluble. So the process of elimination states that 1 probably is the answer. And it is because, remember, silver is one of those, what, exceptions. So let's go to table F just to make sure you understand. Silver chloride would make a precipitate. If silver chloride was made for mixing solutions, okay, you would definitely see it as a solid. Let's go C to make sure that you understand that you can identify silver chloride as a precipitate or a solid or something insoluble from table F. So silver chloride has halides. Halides are soluble. There are some exceptions. What do the exceptions mean? Well, that means it is soluble except when bonded with these ions. Well, silver chloride is one of the exceptions. Therefore, it's an exception to being soluble, meaning it's not soluble. Silver chloride, lead 2 chloride. the dimercury chloride would all be insoluble. So that's how you read that. Now you have exceptions over here. Carbonate ions are usually insoluble except with what? Group 1 ions or ammonium ions. So you have exceptions the other way as well. Make sure you're aware of that. Okay? So clearly 41 is choice 1. All right, now again, you could have got all confused about this whole paragraph. Table F tells you who's soluble, insoluble, so you could just went to table F and see which one was different. Okay, good strategy to do if you do get lost a little bit in the sauce in terms of what they're talking about. All right, so number 42. At standard pressure, the total amount of heat required to completely vaporize a 100-gram sample of water at its boiling point is what? This is tied to an earlier question, and what I'm going to do here is make some space to talk about it, but it's an easy calculation. You just have to remember what you're calculating. So my friends in chemistry, what we would do here is recognize we're vaporizing a sample. Now, the way that I have taught this is that I would show myself a heating curve like we had in the question above, and you notice that if you're at a phase, like this is the liquid phase, you would use MC change of T for your formula to measure the energy, or the Q, to raise the temperature. Remember, this is temperature kinetic energy. Now, if you're at a phase change, which you should be aware is when the kinetic energy is staying the same because we're converting it into potential, you can't use this formula from table T, because that has a what? A change in temperature, and there is no change in temperature at these phase changes. So you have to use another formula. That formula would be mass times the heat of vaporization equals Q. And just as an aside, if you're using how much it takes to melt a substance, that's the heat of fusion, that'd be the mass times the heat of fusion. Now, these things right here are constants given to you. Okay, don't know why that went so big, but hey. So you should be aware of these constants as well. So this question was recognizing that you're at a boiling phase change that requires this formula. Let's go find these formulas. They're given to you in table T. So here we are at table T, and I'm going to scroll down to where I can find my heat equations right here. Okay, so there are my heat equations, and I'm looking for things that help me figure out the heat of vaporization. So I see, oh, H of V is heat of vaporization, and looky here, they give you a formula. Q is equal to mass times heat of vaporization. So if you knew nothing about the heating or cooling curve that I just drew to help you memorize or understand when to use these thermal equations, heat of vaporization is what they're asking how much energy it took to vaporize something. You had to know that this is the formula you used. So you the mass times the heat of vaporization. Now, what is the heat of vaporization? We have to go to another table, and that would be on the first page. So let's go there. So in the first page of your reference table, okay, we can see, and let's just make this bigger, we can see that there is a table called table B, physical constants of water, and we can see the heat of vaporization is 2260. All right, so mass times 2260, whatever the mass would be, is how we would solve this problem. So Q is equal to the mass times the heat of vaporization. Now, what is the mass? That 100-gram sample. Not very difficult math here. And I'm going to times it by that heat of vaporization value that I get from table B, 2260, and that's joules per gram. All I'm doing is multiplying these two values. Put that in our calculator, or you can see that you're just adding two zeros to that, which would be 226000, and that's joules. Okay, the grams would cancel. So which question represents that? Oh my gosh, exponential notation. No big deal. No big deal. Okay, you should learn that the decimal point is right here. To put it into scientific notation, I'm going to move the decimal place how many places? 1, 2, 3, 4, 5. I'm moving it 5 places. Okay, so this number here is the same as number 4. That's all that was. So this was a question that did you recognize that you needed this formula from table T. I think it's best to think of it in terms of, hey, where do I use the formula? I'm dealing with vaporization right here. We don't have a temperature change, so you need this formula. They give you this value in table B. Okay? And then you had to convert this to scientific notation. And of course, number 4 is the answer. If you were to take this number and have 5 zeros get bigger, it would equal the same number here. So number 42 is choice 4. So this question, number 43, a sample of helium gas is in a sealed rigid container. What occurs as the temperature of the sample is increased? Well, we should know that temperature increases, and what's going to happen is the average kinetic energy is going to increase, because as kinetic molecular theory suggests, temperature is proportional to the average kinetic energy. So they're going to move faster. If they're going to move faster, there's going to be the frequency or the amount of collisions between atoms have to increase. All right, you make the molecules move faster, they're going to collide more often, and you're going to increase the number of effective collisions. That's why increasing the temperature increases the rate of reaction. The mass of the sample will not change if you just increase the temperature. The number of moles of the gas will not increase. The helium's not reacting with anything, so there's no new molecules being made. The volume of each atom is not going to decrease. That's not going to change. The only thing that makes any sense is that making them move faster, they're going to collide more often. 43 is 4. Okay, number 44. Number 44 is Le Chatelier's question. You can see right away that we have a double arrow. This double arrow denotes that the rate of the forward reaction equals the rate of the reverse. So the question states, which change, which is called a stress, causes the equilibrium to shift to the right? So what I always teach my students is when you have a Le Chatelier's problem, draw this little graph here. Little graph helps you organize your thoughts. You have the stress, and that's what we do, and there's the response. Now the response represents what the reaction does, and as you probably have already learned, that Le Chatelier's principle states that when you add a stress to a reaction at equilibrium, it's going to respond to do the opposite to regain its balance. I always tell my students, if I have a student who's standing and I push on them, they're going to fall over. So if I push on them in the forward direction here, they're going to fall over unless they do what? Unless they push back opposite to regain their balance. If they don't push back opposite, they fall over. It's the same thing with reactions. We're going to push on them with different stresses, and they're going to push back opposite to regain their balance. They always do the opposite. So the stress is what we do, like pushing the person. The response is the reaction doing the opposite to regain its balance. So we're asking which change causes the equilibrium to shift to the right. Shifting to the right means that the reaction now is regaining its balance by doing that. Shifting to the right is the response. It's tied to the response. Now, why would it shift to the right? It shifts to the right because by doing so, it's going to decrease and use up the reactants to make more of the products, including the heat here. So let's look at the choices. Adding a catalyst. When you add a catalyst, you're going to speed up the forward reaction and you're going to speed up the reverse reaction because you're going to lower the activation energy for both reactions the same. So adding a catalyst is not going to work. It's not going to be. Now adding more O2. So if I was to increase the O2, that's what we do. The response by the reaction to regain its balance is going to lower the O2. Is this shifting to the right, lowering O2? Yeah, it is. By shifting to the right, you're saying we're favoring the forward reaction and more products is going to be made and O2 is going to decrease. So that's your answer. To make sure it's your answer, let's look at the other choices. If you decrease the pressure, there's another stress, decreasing the pressure. Well, the reaction is going to respond by increasing the pressure, which means it's going to shift to make more moles of gas. When you hear the pressure, count moles of gas. This has 2, this is 1, this is 3 moles of gas. This is 2 moles of gas. So what would happen by decreasing the pressure, it would shift to make more moles of gas. And you should know gas molecules, when they collide and move, the pressure is due to the gases colliding. So having more gas molecules would result in more pressure. So number 3 is not the answer, because by decreasing the pressure, the reaction would shift to the left to make more pressure, more moles of gas, and that is not the shift that actually occurs. The other choice that can't be correct, if we were to increase the temperature, the reaction would look to lower the temperature. Now, in truth, it would find a new equilibrium position that favors the endothermic way, but the bottom line here is increasing the temperature, the reaction is going to shift to lower the temperature. It would lower the temperature by using it up and favoring, as I said before, the endothermic way, but this is actually favoring the exothermic way. Look at my arrow. If it's shifting to the right, that means we're making more products, and one of your products is heat. We're increasing the heat. The response would need to decrease the heat if we increase the temperature. So that's why 4 is wrong as well. So it makes sense. People get confused with the increasing, decreasing arrows. Remember, the stress is what we do. The response is what the reaction does by shifting to do the opposite of what we did. So the only correct answer, okay, is increasing the oxygen would cause the reaction to shift to lower it. We increased it, the reaction needs to lower it. The only way you can lower it is favor the forward reaction. Okay, so choice 2 is your answer for number 44. Number 45. This is the first organic question I believe that I have seen in this test. Given the formula representing this compound, what is a chemical name of this formula? So the IUPAC name of this is based on its structure. Structure is king in organic chemistry, because you change the structure, you change its chemical and physical properties. And that's true in inorganic as well, but it really comes to life in organic chemistry because a lot of the compounds have the same number of carbons and hydrogens. There's so many different combinations, but structure is so very important in biochemistry and organic chemistry. In any case, the structure tells me the name. So the first thing that I do when I try to name an organic compound, find the longest continuous chain of carbons. So this will be the first carbon, the second carbon, the third carbon, the fourth carbon, and the fifth carbon. The longest continuous chain is 5. Now we have some tables in the reference tables that tell us something about how to name compounds, and that would be P, Q, and R. Let's go to P right now. So P tells you how to start the prefix. It's the pre-beginning of the name. And we have 5 carbons that we counted. So it's going to begin with a pent. Now I know all the choices had pent in there, but I still wanted you to know where to look for that. Okay, now once we know the number of carbons, we're going to have to figure out what the ending or the suffix is of the beginning part of the name based on what kind of bonds exist between the carbons. So if you go down to table Q, it's going to tell you how to end this, this name in terms of the longest continuous chain. So we have ane, ene, or ein. What we're looking here for is the single for an ane, a double bond for an ene, and a triple bond between the carbons for an ein. So let's go back to our question. So we can see that we have a double bond here. So this tells me that I am dealing with enes, which makes sure that, so now I know that 2 and 4 I can cross out. So the question is it a 2-pentene or a 3-pentene? This is what we have a dilemma here. So we know that when we have, again, structure is king, so knowing where the double bond is important. So we put numbers in front to tell us where things are in our compound. So we know it's a pentene because of the ENE. That's clear. But the problem is it a 2 or 3-pentene? And as you probably have guessed, in the IUPAC naming system, when we describe where things are, we try to put them on the lowest carbon possible. So I numbered this as 1, 2. So therefore, this carbon or this double bond starts at the second carbon. Now, if I numbered my carbons this way, 1, 2, 3, you would say, well, couldn't it start on a third carbon? Absolutely. But just by convention in the naming system, they want you to put the number on the smallest number possible, or write the smallest number possible for describing where things are. So we would say 2-pentene is our best answer here. That gives me the lowest possible number for where this ene is, where this double bond starts. So 2-pentene is the answer. All right, very important. Wherever things are attaching to your carbon chain, you describe where they are in relation to those carbons by the lowest number possible. 45 is 1. Oxidation number of manganese in KMnO4. So we've got KMnO4. Now, when you have 3 elements, you have to realize that it's probably going to be 2 elements that you definitely know their oxidation numbers and 1 that you do not. Let's say I say, listen, okay, number of manganese. Now that's simple. I could say just look up the charge in the periodic table. So let's go there. So for manganese, you can see that I can't start with it. It has multiple charges. Okay, so I'm going to have to figure out which charge it is based on the others. Now, if I go to oxygen, it's a good place to start because oxygen only has one choice you can start with, and that's -2. Okay? And then the potassium, a group 1 ion, way over here, only has one choice it can become, and that's +1. So I'm going to start with the ones I definitely know that only have one choice to get to the ones that have multiple. So let's go back to the problem. So in order to find the charge in the manganese in this compound, I have to realize there is no charge overall written for this thing. This is not a polyatomic ion. It's a compound, and they have to be neutral. So what I do is I make the whole thing equal to 0 because I know the whole thing has to equal 0. Now, if it's a polyatomic ion, let's say like a nitrate ion, it'd have to equal to -1, but that's not the case here. Just be aware of that. Okay, so I'm going to start with the ones I know. I know that potassium is +1 individually. So since there's only what? One of them, it's +1 overall. Okay? Now, oxygen is -2 individually. We got this right from the periodic table. The charge it likes to become, upper right-hand corner, we just saw them. Now I have 4 of them. So the overall charge due to all the oxygens is going to be -8. Okay? So if you separate your elements here in the compound, you will see what charge do I need plus a +1 and a -8 to give me 0. I'll say that again. What number plus a -8 and a +1 gives me 0? If you have to use a calculator, be my host. Get this question right. But the answer to this is +7. +7 plus 1 is +8 plus a -1 is 0. Since there's only one Mn here, it's +7 individually. So we're looking at choice 1 as our answer. So I use the what? The ones I definitely knew individually. Then I use the overall charges of them equaling this number to find the individual. Okay? Any case, 46 this is the first skill you have to have in redox is assigning oxidation numbers. 46 is clearly 1. 47. When the pH of an aqueous solution is changed from 1 to 2, the concentration of hydronium ions of the solution is. Okay, what is a hydronium ion? Hydronium is H3O+. It's a water holding on to a proton. Now it sounds a lot like a hydroxide, so you can get this wrong if you think it's a hydroxide. You need to know that H3O+ is due to acids create this scenario in water. Why? Because let's say you take hydrochloric acid and you have water. As you learn in one of the other definitions of an acid, acids donate their protons. It could donate the H+ that they give off, and it makes H3O+. So this clues you in that we're talking about what's happening to the acid nature of the water. Now, if you didn't know hydronium was H3O+, Check, there's a place to look. Let's go there. So table E is your friend, and there we go. The hydronium ion is the H3O plus. Sounds a lot like the what? The hydroxide. Don't get them confused. This is the basicity part of the water equilibrium. This is the acidity part. Very important that you knew that H3O plus is the acidity part, the hydronium ion. So now that we have that established, okay, they're talking about what's happening to the H3O plus. We should now know that the pH changed from 1 to 2. So the pH is increasing, and you should be aware that the basicity part of the pH range is 7 and beyond, 7 and higher. So as the pH rises, you're getting more basic, which means the hydroxide part of the water-based equilibrium is increasing, and this must be decreasing. So that's why we can get rid of increasing. The hydronium is not going to increase because we're getting less acidic, right? pH 7 and beyond. Now, for those that don't understand, okay, what you should understand is, let's pretend, I don't want to do the negative logs here, but the idea here is that if the concentration of your acid of H3O plus is 1 times 10 to the negative 1, which is the same thing as 0.1 of the H3O plus, the pH of this is always the positive value of this. This is the pH of 1. So you get a pH of 1 from this. All right, and if you remember from your class, you took the positive value of this number, so the pH is 1 here. Now, if the concentration decreases to 1 times 10 to the negative 2, that means now you have a 0.01 solution. And if this is the concentration of H3O plus, now the pH is 2. What's happening as this number gets smaller, your pH, which is the positive value of this exponent, is getting bigger, and that's why it works. So as the H3O plus concentration drops, this pH number increases. All right, so we're getting less acidic. Now the next question is, and this is very important, am I decreasing by a factor of 2 or by a factor of 10? Well, we know we're going down because obviously the concentration is dropping. We're becoming less acidic as the pH rises, and I don't care if you don't understand the math here. You should know as pH rises, you're getting closer to a neutral solution and eventually a basic solution, right? Neutral is a 7, then a basic is what? Above it, and acidic is below it. So if you don't get the math here, as pH rises, you have to know you're getting more basic and less acidic. This is due to acidity. So that's why the acidity of the H3O plus is decreasing. However, by what factor? pH, you have to know, is basically an exponent. So when you go from a pH of 1 to 2, you're changing 10 times. Each individual movement of a pH integer is a 0 because it's a log in base 10. So this is changing, you can see, 10 times. So if you go from pH of 1 to 2, the number changes, or you would say, wow, it's doubling. It's not doubling. You're increasing by 1 pH, and 1 pH is 1 exponent base 10. So it decreases by a factor of 10. Tricky question there. So we would say that the acidity decreases because the pH is rising, and because it moves from a pH of 1 to 2, that means you're moving 10 times. Each movement. If I went from a pH of 1 to 3, you could see that that is going to be a movement of 2, which is really 10 to the 2, which would be 100 times. If I went from a pH of 1 to a 4, you can see that's a movement of 3 pH integers, which is really 10 to the 3, which is 1,000 times. Okay, so each movement from one integer to the other is an exponent in the base 10 system. All right, very important you understand that. And I'm sure you went over that at length in your course. So 47 is choice 2. What is the color, number 48, what is the color of the indicator thymol blue in a solution that has a pH of 11. Well, we should know that's a basic solution. It's above 7. But thymol blue is an indicator in table M. So we've got to go there. They didn't tell you that. You should know table M is where you want to go, and here we go. So thymol blue in table M is an indicator that changes color in the presence of different pHs, and you see that the pH is 11. So what that means is that anything 9.6 and greater is going to be blue. So when you read table M, when they give you these ranges, 9.6, that would mean anything above 9.6 is blue. The 8.0 and lower represents the yellow. So if you look at this like methyl orange, circle this one and go this way. Anything 3.1 and lower is the red. Anything 4.4 and higher is yellow. So in any case, you're just reading off table M, you had to know, you had to go here. Clearly, it is blue. 48 is blue. Number 2. Number 49, more organic chemistry. Which formulas represent compounds that are isomers? Iso means same. That means the same chemical formula, but different structure. Structure is king. So I can get rid of choice 1. This is CH4, and this is C2H6. These guys have different chemical formulas. They have to have the same number of stuff, but a different structure. Now you may say, well, number 2 looks like they're different structures and the same number of stuff. Right, they're both CH40, okay? But they are the same structure. If you take this one and peel it backwards this way, pick it up and flip it over, it's the same structure. So they have to have different structures, therefore different properties, but the same number of stuff in them, okay? So you can see we can cross out number 4 because you have 4 carbons here and 2 carbons here. So number 3, both of these have the same number of stuff, C3, okay, H, I believe 8. 1, 2, 3, 4, 5, 6, 7, 8. I should believe myself. And 1 oxygen. Oops, what was that? Okay, and 1 oxygen. And this one is also C3, and you can count H8 and 1 oxygen. You do not want to get this one wrong again if this is one of the ones that you're reviewing. So clearly these both have the same number of atoms and types of atoms, but different chemical, a different structure, a different arrangement, and that's what an isomer is. Choice 3 is your answer for this question. Nice organic question. We like these. Very common one too. Number 50, one beneficial use of a radioisotope. Now, radioisotopes are just fancy words for elements that are radioactive. So, radioactive. This is a nuclear chemistry question. And this is one of the things you just kind of have to know. But you should know this anyway. Okay? We use radioisotopes, radioactive elements, okay, to detect diseases. And what we do is we can use them as tracers, okay? For instance, a PET scan, okay? If you haven't heard of a PET scan, and it's called PET, and the acronym PET means positron emission topography scan. So what we do is we give people something called nuclear medicine, which is radioactive atoms or molecules, and they have very, very short half-lives. It's very important that you know this. The short half-lives mean that they decay out of the body very quickly, but during the time they're in our body, they emit, in the case of PET scans, they're emitting positrons, and these positrons, which are basically antimatter or the opposite of an electron, they hit electrons, and when they hit electrons, electromagnetic radiation is given off that the detector can figure out. And from the location of where these electromagnetic radiation is given off, they can actually get a three-dimensional image of the brain. It's one of the best ways we can get an image of the brain. But in any case, these atoms give off radiation or different types of particles as they try to get stable. And we use this emission of radioactivity as a way to trace where the atoms are going or how hard they are to travel to a certain position. We can look at the vascularization or those kind of things. So detection of disease is a big use of radioactive elements in terms of ones that are safer for the body because of their shorter half-lives. Neutralization of an acid spill is an acid-base thing. Decreasing the dissolved O2 and level in seawater could be a solubility issue. All right, and same thing with 4. So radioisotopes, you should be aware, they're very helpful in diagnosing and tracing what's wrong with the body, and they have low health risk because of their short half-lives, meaning it takes with a short half-lives, that means it gets out of your body quickly, and that's something you should have talked about in your nuclear chemistry section of your course. So number 50 is 1.